Hello there, you're listening to the planet's memory, where time breathes and the earth remembers. Close your eyes and let yourself drift into a story that exists beyond the edges of everything you thought you knew about our world. Tonight we journey into the deepest mysteries that sleep beneath our feet, hidden in layers of rock and time, waiting to whisper their secrets to those patient enough to listen. Imagine a time before humans walked this earth, before our civilizations rose and fell, before our ancestors even dreamed of fire or language. Imagine a world where something else held dominion, where intelligence flourished in forms we cannot fathom, where a war so devastating unfolded that it literally reshaped the surface of our planet and left scars that remain visible even now, millions of years later. This is not fantasy, not fiction spun from imagination alone. This is the story written in stone, carved into the very bones of Earth itself, preserved in geological formations that defy conventional explanation and archaeological anomalies that challenge every assumption we hold dear about the history of life on this planet. The evidence surrounds us, scattered across continents, buried beneath oceans, frozen in ice, and yet we walk past it every single day, without seeing, without understanding, without recognizing that we live on a battlefield where titans once clashed in a struggle that makes our human conflicts seem like the quarrels of children. Tonight, let these words carry you into that ancient darkness, into that silent war, into a past so remote that time itself struggles to measure it. Let your breathing slow, your muscles relax, your mind open to possibilities that textbooks dismiss and scientists whisper about only in private. This is your invitation to witness something extraordinary, to explore evidence that has been waiting patiently for millions of years to tell its story. The silent war is not silent anymore. Listen closely now as we begin to uncover what happened here long before we arrived in the world that was. The story of Earth is far older and stranger than most people ever imagined during their waking hours. And tonight, as you settle into the comfort of rest, we invite you to consider that the planet beneath you holds memories of events so profound that they challenge the very foundations of what we think we know about our home. For over 4.5 billion years, Earth has been witness to transformation upon transformation, from a molten ball of cosmic debris to a living world teeming with complexity. But somewhere in that vast expanse of time, something happened that does not fit neatly into the narratives we were taught in school. There are marks on this planet, signatures written in geology and biology, that suggest periods of catastrophic violence on scales almost impossible to comprehend. These are not the slow grinding changes of continental drift alone, not merely the patient work of erosion and uplift, but sudden, devastating events that reshaped entire regions in moments, that drove countless species to extinction, that left behind evidence of forces and technologies that should not exist in the time periods where we find them. Scientists have long recognized that Earth's history includes several mass extinction events, moments when the vast majority of life on the planet vanished in geological instants. But the conventional explanations for these catastrophes have always felt incomplete to those willing to look more carefully at the evidence. Asteroid impacts certainly occurred, volcanic eruptions on unimaginable scales definitely happened, climate shifts radically altered environments again and again, but some of the patterns we observe, some of the physical evidence we uncover, points towards something more deliberate, more intelligent, more purposeful than random cosmic accidents or natural disasters alone can explain. Consider for a moment the strange fact that certain layers of rock across multiple continents show evidence of having been subjected to temperatures far higher than any natural process should produce. Consider the mysterious spherules of perfectly formed metallic compounds found in strata dating back hundreds of millions of years, objects that resemble nothing so much as the residue of advanced manufacturing processes. Consider the anomalous isotope ratios that appear in sediments from specific time periods. signatures that in modern contexts we associate exclusively with nuclear reactions. Consider the massive structures found deep underground in various locations around the world. Geometric formations that some researchers argue display characteristics of artificial construction rather than natural formation. Consider the peculiar distribution of certain rare elements in concentrations and patterns that geological processes alone struggle to explain. Consider the evidence of massive, rapid changes in sea levels and land masses that occurred far too quickly for plate tectonics alone to account for. All of these pieces of evidence exist, documented in scientific literature, though often dismissed or explained away through conventional frameworks that refuse to entertain more unsettling possibilities. Tonight, we gather these threads together and follow them into a hypothesis that some researchers have begun to voice more openly in recent years: the possibility that Earth was once home to intelligent life before humanity, perhaps more than once, and that at least one of these pre-human civilizations engaged in a conflict so devastating that it nearly destroyed all life on the planet and certainly reshaped the world in permanent ways. This is not about ancient aliens visiting from other worlds, though that possibility remains open for consideration. This is about the evidence suggesting that Earth itself, this planet we call home, may have nurtured intelligence long before primates descended from trees, long before mammals dominated the landscape, perhaps even before the age of dinosaurs. Its amazing scales involved are so vast that they challenge human comprehension. Millions upon millions of years during which entire ecosystems rose and fell, during which continents rearranged themselves, during which the very atmosphere of the planet transformed from one chemical composition to another. In such vast stretches of time, life had countless opportunities to experiment with different forms, different strategies, different evolutionary paths, and intelligence is simply one particularly effective survival strategy among many. If intelligence emerged in humanity after only a few million years of primate evolution, why should we assume it never emerged before in the hundreds of millions of years of complex life that preceded us? The assumption that humans represent the first and only intelligence this planet has produced is not based on comprehensive evidence, but rather on absence of evidence. And as any scientist knows, absence of evidence is not evidence of absence, especially when we are looking back across time spans so enormous that conventional fossilization would preserve only the tiniest fraction of what once existed. The silent war that we explore tonight is a war evidenced by catastrophic destruction, by strange artifacts, by geological anomalies, by extinctions that occurred with suspicious precision, by evidence of energy releases that dwarf anything natural processes alone can produce. It is a war that appears to have reached its climax during what geologists call the Permian-Triassic boundary, approximately 250 million years ago, when something like 96% of all marine species and 70% of terrestrial vertebrate species vanished from the Earth in what represents the most severe extinction event in our planet's known history. The conventional explanation involves massive volcanic eruptions in Siberia, combined with climate change and ocean acidification, and certainly these factors played roles. But when we examine the evidence more closely, when we look at the patterns of destruction and the strange residues left behind, we find signatures that suggest something more than volcanism alone. We find evidence of warfare. We find evidence of weapons. We find evidence of a conflict that consumed the world and left almost nothing alive when it finally ended. Tonight, as you drift towards sleep, let us walk together through this evidence, piece by piece, layer by layer, until a picture emerges from the darkness. A picture of Earth's hidden history, of the silent war that reshaped everything, of the conflict that nearly ended all life on this planet, before humanity ever had a chance to exist. Understanding the story we are about to explore requires first grappling with a concept that human minds find deeply difficult to truly comprehend, and that concept is deep time. Deep time refers to the vast geological timescales across which Earth's history unfolds. Periods so lengthy that human history, all of recorded civilization, all of our wars and empires and religions and art, represents less than a blink in comparison. Modern humans, Homo sapiens, have existed for perhaps 300,000 years. All of human civilization, from the first agricultural settlements to the present moment, spans only about 12,000 years. Writing has existed for maybe 5,000 years. Our entire species, everything we think of as humanity and human achievement, occupies a sliver so thin in the timeline of Earth that it would be almost invisible if we drew that timeline to scale. Now, stretch your imagination backward, past the emergence of humans, past the age of mammals that followed the extinction of dinosaurs 66 million years ago, past the entire age of dinosaurs that stretched for over 160 million years before that, past the first forests and the first animals to walk on land, past the Cambrian explosion when complex multicellular life first diversified in dramatic fashion, all the way back through billions of years when Earth was the domain of microorganisms alone. The planet is approximately 4.5 billion years old. Complex multicellular life has existed for perhaps 600 million years. The dinosaurs lived between roughly 230 million and 66 million years ago. In between these vast stretches, entire worlds rose and fell. Ecosystems appeared and vanished. Species evolved and went extinct by the millions. The challenge of deep time is not just intellectual but also practical. When we look for evidence of ancient civilizations, we typically look for structures, for artifacts, for remains that have survived weathering and geological processes. But Earth is extraordinarily efficient at recycling its surface materials over long time periods. The oldest rocks on Earth's surface are only about 4 billion years old, and these are exceptionally rare survivors. Most of Earth's surface is far younger, constantly renewed through plate tectonics, volcanic activity, erosion, and sedimentation. The ocean floor, which covers most of the planet's surface, is nowhere older than about 200 million years because it is continuously created at mid-ocean ridges and destroyed at subduction zones where tectonic plates dive back into the mantle. This means that any evidence of activity on Earth's surface from more than 200 million years ago has either been buried under kilometers of newer sediment, melted and recycled into the mantle, thrust upward into mountain ranges where erosion has worked at it for millions of years, or otherwise transformed beyond easy recognition. The fossilization of organic remains is an exceptionally rare occurrence requiring very specific conditions that preserve tissues before they decompose, and even then, only the hardest parts like bones and shells typically survive, and even those only under the right chemical conditions. Soft tissues, behavior, culture, technology made from materials that degrade quickly, all of this vanishes almost instantly on geological timescales. If human civilization were to vanish today and some observer came to look for evidence of our existence 10 million years from now, they would find very little. Some of our stone structures might remain as puzzling formations. Some of our synthetic materials might persist as strange chemical anomalies in certain strata. Perhaps some of our deepest mines and tunnels would still exist as voids in the rock. But the vast majority of what we consider human civilization, our cities and roads and artifacts, would be gone, ground to dust and scattered by the patient work of geology. This is the deep time problem. If we struggle to imagine what evidence would remain of humanity after 10 million years, how can we possibly hope to find clear evidence of intelligent civilizations that might have existed 50 million or 100 million or 200 million years ago? And yet, despite these challenges, there are clues. There are anomalies. There are patterns in the geological record that do not quite fit the comfortable narratives of purely natural development. These anomalies cluster around certain time periods, suggesting that something unusual was happening at those moments in Earth's history. The scientific method requires us to examine evidence wherever it leads, even when it leads to uncomfortable conclusions that challenge our assumptions. For most of the past century, the assumption that humans represent Earth's first intelligent species has been so deeply embedded in scientific thinking that evidence to the contrary has been dismissed almost reflexively, explained away through conventional means, or simply ignored as too speculative to warrant serious attention. But science progresses by questioning assumptions, by following evidence even into strange territory, by entertaining hypotheses that seem unlikely until they can be properly tested. In recent decades, a small but growing number of researchers have begun to ask a simple question. If an industrial civilization had existed on Earth millions of years before humanity, what evidence would it leave behind? And would we even recognize that evidence if we found it? This question, explored seriously rather than dismissed as science fiction, leads to fascinating and troubling places. The Silurian hypothesis, named playfully after a science fiction race, but explored seriously by scientists including Gavin Schmidt and Adam Frank in a paper published in the International Journal of Astrobiology, examines exactly this question of detectability. What markers would an ancient industrial civilization leave in the geological record? The answer is both surprising and sobering. Very few permanent markers that would be unambiguous after millions of years, but some potential signatures do exist. Rapid increases in certain isotope ratios, particularly carbon isotopes that indicate massive burning of fossil fuels, might be detectable. Increases in certain synthetic molecules that do not occur naturally would be preserved in sediments. Sudden changes in the distribution of rare earth elements, spikes in heavy metals, evidence of rapid global warming followed by ecological collapse, layers showing massive species extinctions coinciding with other anomalous chemical signatures. Perhaps most tellingly, evidence of rapid increases in global temperatures and carbon dioxide levels that correspond with geological moments of extreme extinction events. The fossil record does show several periods where exactly these signatures appear. Moments when the climate changed with extreme rapidity, when carbon dioxide spiked suddenly, when extinction cascaded through ecosystems, when the chemistry of oceans and atmosphere shifted in ways that suggest not just natural volcanism but something else, something that consumed resources and released byproducts on scales comparable to modern industrial civilization. The Permian Triassic extinction event, the worst of all known mass extinctions, shows many of these signatures. So do several other major and minor extinction events scattered through the past few 100 million years. Could these be the fingerprints of ancient industrial civilizations that rose and destroyed themselves or each other? The possibility cannot be dismissed out of hand. Let yourself relax into this uncertainty as we explore it together through the night. There is something peaceful about acknowledging the vast mysteries that remain unsolved, about accepting that the universe and our planet hold secrets far deeper than our current understanding encompasses. The deep time problem means we will never have perfect certainty about events from hundreds of millions of years ago, but we can gather evidence, look for patterns, and construct hypotheses that fit the data better than conventional explanations alone. As you breathe slowly and feel yourself drifting, imagine the layers of time like layers of sediment, each one covering the one below, each holding fragments of stories mostly lost but not entirely erased. Somewhere in those layers, if we know how to read them, the evidence of the silent war awaits our discovery. The war was not silent because it was quiet, but because time has muffled its echoes, has buried its battlefields, has scattered its participants to dust and memory. But silence is not the same as absence. The scars remain, written in stone, preserved in chemistry, visible to those who know how to look. In this first chapter, we establish the foundation for everything that follows. Earth is far older than human intuition grasps. Evidence from deep time is fragmentary but not non-existent, and the assumption that humans are Earth's first intelligent species is just that. an assumption rather than a proven fact. With this foundation in place, we can now begin to examine specific evidence that suggests something remarkable and terrible happened here long ago, something that reshaped our world and determined the conditions under which humanity would eventually emerge. Approximately 252 million years ago, at the boundary between the Permian and Triassic periods, Earth experienced what scientists call the Great Dying, an extinction event so severe that it nearly ended complex life on this planet. The numbers associated with this catastrophe are staggering and difficult to truly comprehend. Roughly 96% of all marine species vanished. Approximately 70% of terrestrial vertebrate species disappeared. 83% of genera across all environments went extinct. This was not a gradual decline, but a catastrophic collapse that, based on geological evidence, occurred over perhaps 60,000 years, which is instantaneous in geological terms, though it would span countless generations for the creatures living through it. The oceans became toxic wastelands with vast dead zones devoid of oxygen. The atmosphere filled with greenhouse gases that sent global temperatures soaring by 10 to 15 degrees Celsius, possibly more. Acid rain fell from skies choked with volcanic aerosols. The chemical balance of the ocean shifted so dramatically that shells and coral skeletons dissolved in the acidified waters. Life clung to survival in only the most marginal environments, in caves and deep underground, in isolated pockets where conditions remained just barely tolerable. And for millions of years afterward, Earth's ecosystems remained impoverished and struggling, showing little diversity or innovation as the planet slowly healed from whatever had devastated it so completely. The conventional scientific explanation for the Permian-Triassic extinction centers on the Siberian Traps, a massive volcanic province in what is now Russia, where millions of cubic kilometers of lava erupted over a period that coincides with the extinction event. These eruptions would have released enormous quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere, triggering greenhouse warming, acid rain, and ocean acidification. The lava also erupted through coal beds and evaporite deposits, potentially releasing even more greenhouse gases, including methane, and causing runaway climate change. This explanation has significant evidence supporting it and is widely accepted among geologists, but it has always had some puzzling aspects that researchers have struggled to fully explain. The volcanic eruptions alone, while massive, do not quite seem sufficient to cause extinction on the scale observed. There have been other large igneous provinces in Earth's history that did not cause such extreme extinctions. The pattern of extinction shows some curious features, including the fact that some groups of organisms went completely extinct while closely related groups survived, suggesting something more selective than just global environmental catastrophe. The chemical signatures in the rocks from this period show some anomalies that volcanism alone does not entirely explain, particularly certain spikes in elements and isotopes that appear in concentrations difficult to account for through natural processes alone. When we examine the Permian-Triassic boundary layers more carefully, looking specifically for evidence that conventional geology might overlook or misinterpret, we begin to find curious details that suggest a more complex story. In multiple locations around the world, the boundary layer contains tiny spherules, perfectly round microscopic droplets of melted and rapidly cooled minerals that some researchers argue resemble the residue of extremely high temperature events, potentially even nuclear reactions. Conventional geology interprets these as impact spherules from meteorite strikes, or as volcanic products, and certainly some of them are, but the distribution and composition of others does not fit these explanations as neatly as one might hope. There are spikes in iridium and other platinum group elements at the boundary, which are typically interpreted as evidence of asteroid impact, and there may well have been impacts during this period. That the patterns of distribution and the ratios of different elements show some irregularities that have puzzled researchers who have studied them closely. There are also anomalies in the ratios of uranium isotopes and other radioactive elements that some scientists have quietly noted do not match what natural deposits should show. In a few locations, there are thin layers of what appears to be glass formed from sand or rock melted at temperatures exceeding what any known volcanic process can achieve and then cooled rapidly, a pattern that in modern contexts we associate with nuclear detonations or certain advanced industrial processes. Perhaps most intriguingly, when we map the locations of the most extreme environmental disruption and extinction during the Permian-Triassic event, we find that the devastation was not entirely uniform across the planet, but instead shows certain patterns that suggest focal points of destruction from which damage radiated outward. The Siberian Trap's volcanism was certainly one such focal point, but there are others, including areas in what is now China, southern Africa, and parts of the ancient supercontinent Pangaea, that show evidence of catastrophic environmental collapse that seems to exceed what distant volcanic eruptions alone should cause. Some researchers have proposed that the Siberian Trap's volcanism itself might have been triggered by something else, perhaps an asteroid impact on the opposite side of the planet that sent shockwaves through Earth's mantle. But the evidence for such an impact remains ambiguous. What if the volcanism was triggered not by random impact, but by deliberate action, by weapons of unimaginable power used in a war between factions or species that had the technology to literally crack the planet's crust and unleash the fires below? What if the chemical signatures we find in the boundary layer represent not just volcanic gases and impact residues, but also the byproducts of advanced weapons, the fallout from energy releases that make nuclear bombs look like firecrackers, the scattered remains of technologies we cannot even imagine? This is speculation, certainly, but it is speculation grounded in real anomalies, in evidence that does not quite fit conventional frameworks, in patterns that suggest intelligence and purpose rather than random catastrophe alone. As you lie comfortably and feel yourself drifting deeper into rest, let your mind wander through this ancient catastrophe. Imagine a world burning, oceans dying, skies darkening with ash and worse than ash, the scattered survivors of a war that destroyed everything they had built and nearly destroyed the planet itself. Imagine the weapons that could cause such devastation. Not primitive tools, but technologies so advanced that they could manipulate the very geology of Earth, that could trigger volcanic eruptions, that could release energies sufficient to kill nearly all life. Imagine the desperation that would lead to using such weapons. The conflict that had escalated beyond any possibility of restraint or mercy. The silent war reached its terrible climax at the Permian-Triassic boundary, and what we find in the rocks from that time is evidence of destruction on a scale that should give us pause, that should make us question our assumptions, that should remind us that intelligence is a dangerous gift that has perhaps destroyed itself on this planet before and might do so again. The Great Dying was not just a natural disaster, but potentially the final chapter of a war that had raged for who knows how long, a war that ended when there was almost nothing left to fight for and almost no one left to fight. The rocks remember what we have forgotten, and if we learn to read the language written in their layers and their chemical compositions, they tell us stories that challenge everything we thought we knew about our planet's past. Geology is often thought of as the study of slow processes, of mountains rising millimeter by millimeter over millions of years, of canyons carved grain by grain through patient erosion, of continents drifting at the speed fingernails grow, but geology also preserves evidence of catastrophe, of moments when the slow, patient processes were overwhelmed by sudden violence. And it is in these moments that we find the most intriguing clues about the Silent War. When researchers examine rock samples from key periods in Earth's history using modern analytical techniques, they sometimes find chemical signatures that are difficult to explain through conventional natural processes alone. These signatures appear as unusual concentrations of certain elements, as unexpected ratios of isotopes, as distributions of materials that seem to require energies or conditions that should not exist in the time periods where we find them. Science proceeds by proposing explanations for observations, and generally the simplest explanation that fits the known facts is preferred. But when simple explanations require us to make multiple ad hoc assumptions, or to ignore awkward details, it may be time to consider more complex hypotheses, even if those hypotheses challenge comfortable assumptions. One class of anomalies that appears repeatedly in certain geological layers involves what are called refractory elements, materials that require extremely high temperatures to melt or vaporize, and that typically only concentrate in specific ways through processes like magma differentiation or meteorite impact. In some boundary layers associated with major extinction events, particularly the Permian-Triassic boundary but also others, we find concentrations of refractory elements in forms and distributions that are difficult to fully explain through volcanism or impact alone. The platinum group elements including iridium, osmium, platinum and others appear in spikes that are typically interpreted as evidence of extraterrestrial impact, and certainly Earth has been hit by large asteroids and comets throughout its history. But the ratios between different platinum group elements in some of these spikes do not quite match what we see in known meteorites, and the distribution of these spikes across different geographical locations sometimes shows patterns that are hard to explain if they all came from a single impact. Could some of these anomalies represent not meteorite residue, but rather the byproducts of advanced technological processes? Perhaps even the residue of nuclear or more exotic reactions. The suggestion seems far-fetched until we remember that uranium and thorium, the heavy radioactive elements that power both nuclear reactors and nuclear weapons, are themselves concentrated through natural processes in specific types of ore deposits, and an advanced civilization mining and processing these elements would leave chemical signatures in the environment around their industrial sites. In several locations around the world, researchers have found ancient uranium deposits that show isotope ratios indicating that nuclear fission reactions occurred naturally in these deposits billions of years ago. The famous example being the Oklo natural nuclear reactors in Gabon, Africa, where water-moderated fission reactions occurred about 2 billion years ago and ran for hundreds of thousands of years before the deposits were depleted. These natural reactors prove that nuclear fission can occur without human technology given the right geological conditions, but they also demonstrate that nuclear reactions leave distinctive isotope signatures that persist for billions of years in the rocks where they occurred. If an advanced civilization had developed nuclear technology and used it either for power generation or as weapons, the signatures would look similar, but would appear in geological contexts and time periods where natural reactors should not be possible. Some researchers have pointed to uranium deposits in various locations that show isotope anomalies suggesting fission reactions occurred at times when the geological conditions should not have permitted natural reactors. And while these findings are controversial and often disputed, they have not been entirely explained away by conventional geology. The presence of certain fission products, elements that are produced only by nuclear reactions and that do not occur naturally in significant quantities, in trace amounts in sediments from specific time periods, is another potential marker. Though proving that these traces are not contamination from more recent sources is extremely difficult. Another set of chemical anomalies involves what are called fullerenes, carbon molecules arranged in hollow, spherical, or cylindrical shapes that form only under very specific high temperature and high pressure conditions. Fullerenes have been found in impact craters, in certain types of volcanic formations, and in some meteorites, but they have also been found in boundary layers associated with major extinction events, particularly trapped inside them are noble gases like helium and argon, with isotope ratios that suggest extraterrestrial origin, which is typically interpreted as evidence that the fullerenes formed during asteroid impacts and trapped solar wind gases from the meteorite material. However, fullerenes can also form in the extreme conditions of explosions, fires, and high-energy events, and some of the fullerenes found in extinction boundary layers have characteristics that are ambiguous regarding their origin. Could some of them have formed not in impact events but in the fireballs of ancient weapons? The question is difficult to answer definitively, but it is worth asking. The presence of what appears to be partially vitrified sand and rock in scattered locations around the world, ancient glass formed from melting and rapid cooling of geological materials, also raises questions. Natural processes can create such glasses through lightning strikes, meteorite impacts, and volcanic activity, but the scale and distribution of some ancient vitrified materials, particularly those found in association with the ruins of what might be ancient settlements or structures, has led some researchers to propose that advanced weapons might have created some of them. The chemistry of mass extinction events also shows patterns that are difficult to explain through volcanism alone. The rapid global increase in carbon dioxide and the associated warming that characterizes several major extinctions, particularly the Permian-Triassic event, happened faster than volcanic outgassing alone seems capable of producing, according to some models. There are signs that vast quantities of organic carbon were suddenly oxidized, burned or decomposed in a geological instant, releasing carbon into the atmosphere and oceans at rates that suggest something more than just volcanic heat triggering gradual warming and ecosystem collapse. What could burn or oxidize organic matter on a global scale in a geological instant? Forest fires certainly, triggered by volcanic eruptions or impacts, would contribute, but the scale of carbon release seems to exceed what fires alone can explain. Some researchers have proposed massive releases of methane from frozen deposits in the oceans and permafrost, triggered by initial warming and then causing runaway greenhouse effects. And this certainly played a role, but the initial trigger for the warming remains somewhat unclear. If massive explosive weapons were used during a global conflict, the firestorms and thermal effects would ignite fires across entire continents, would vaporize organic matter in the immediate blast zones, and would release enormous quantities of carbon dioxide and other combustion products into the atmosphere. The chemical signature of such an event would look remarkably similar to what we actually observe in the extinction boundary layers: sudden carbon spike, global warming, ecosystem collapse, ocean acidification, mass death. Let yourself sink deeper into rest as we contemplate these chemical clues scattered through the rocks like words in a coded message waiting to be deciphered. The evidence is fragmentary, ambiguous, open to multiple interpretations, but it exists, and it forms patterns that suggest something more than just natural disasters alone. The silent war, if it occurred, would have used weapons and technologies that released enormous energies, that involved nuclear reactions or even more exotic processes that scattered distinctive chemical signatures across the planet, and those signatures would persist for hundreds of millions of years in the rocks, faint but detectable, if we know what to look for and if we are willing to consider interpretations that challenge conventional thinking. Science requires skepticism, requires us to demand extraordinary evidence for extraordinary claims, but it also requires us to follow evidence wherever it leads, and to be willing to revise our understanding when new data or new interpretations better fit the observations than old models do. The chemistry preserved in Earth's rocks from critical periods of catastrophic change tells a story that does not quite fit the comfortable narrative of purely natural disasters. And tonight, as you drift in the borderlands of sleep, let that discomfort be the doorway to deeper understanding, to seeing our planet's history in a new and more mysterious light. The surface of Earth that we walk upon and build our cities on represents only the thinnest skin of the planet, and much of what has happened in Earth's long history is hidden beneath that surface, buried under sediments or thrust into the depths through geological processes that continuously recycle the crust. When we dig deep or when we explore using remote sensing technologies that can peer into the ground, we sometimes encounter structures that puzzle researchers, formations that seem too regular, too geometric, too purposeful to be easily explained as natural creations. And while the vast majority of these can eventually be explained through conventional geology, a few remain ambiguous, sitting on the borderline between natural and artificial. The question of how to distinguish an ancient artificial structure from a natural formation is far more difficult than it might first appear, especially when dealing with timescales of millions of years during which weathering, erosion, tectonic forces, and other geological processes have worked on any structure continuously. Even if an advanced civilization had built vast cities and monuments millions of years ago, the relentless grinding of geology would reduce most of their works to rubble, would bury that rubble under layers of sediment, would compress and alter it through heat and pressure, would fold and fracture it through tectonic movement, until what remained would be fragments of foundations, puzzling geometric patterns in the rock, anomalous voids or concentrations of materials that do not quite fit natural explanations but that are not definitively artificial either. There are several locations around the world where researchers have found underground structures or anomalies that have sparked debate about possible artificial origin, though scientific consensus attributes most or all of these to natural processes. In South Africa, deep gold mines have occasionally encountered what some miners and researchers describe as walls or tunnels that seem too straight or too regular to be natural fractures or cave systems, though geologists generally explain these as unusual but natural formations created by specific patterns of stress and mineralization in the rocks. In various parts of the world, ground-penetrating radar and seismic surveys have detected voids and regular patterns deep underground that might be natural cave systems or might conceivably be something else, though distinguishing between these possibilities is extremely difficult without excavation, which is often impossible at the depths involved. Satellite imaging, using techniques that detect subtle variations in gravity, magnetism, and subsurface density, have revealed geometric patterns and anomalies in certain regions that some researchers argue could indicate buried structures. Though again, natural geological processes can create regular patterns under some circumstances. The ocean floors, which cover most of Earth's surface and which are very poorly mapped at high resolution, show intriguing features in the few areas that have been surveyed in detail, including what appear to be geometric formations, straight-line features, and regular patterns that might be geological but that have sparked speculation about possible artificial origin. One particularly intriguing class of underground features involves what are sometimes called tunnel systems or cavity networks that appear in certain ancient rock formations. Some of these are definitely natural caves formed by dissolution of limestone or by lava tubes or by other well understood processes, but others occur in rock types where such natural processes should not produce extensive tunnels, and the tunnels themselves sometimes show characteristics that are difficult to explain naturally. In several locations, explorers have reported tunnel walls that appear smooth or even vitrified, as if exposed to extreme heat, that melted the surface of the rock and then cooled quickly into glass. And while volcanic processes can produce similar effects, the context of some of these tunnels does not fit volcanic explanations easily. There are reports of tunnels extending for kilometers in surprisingly straight lines, which is unusual for natural caves that typically follow the easiest paths through rock and therefore tend to meander and branch irregularly. Some tunnels are found at depths where natural formation would require mechanisms that are not well understood. The age of these tunnels is usually impossible to determine directly because rock does not form in tunnels but rather is removed to create them. So we can only date the surrounding rock and say the tunnels are younger than that. But if the surrounding rock is hundreds of millions of years old, the tunnels could be anywhere from recent to almost as old as the rock itself. The interpretation of these subsurface anomalies is contentious, with mainstream geology generally favouring natural explanations and a small minority of researchers arguing that at least some features might warrant consideration of artificial origin. The challenge is that after millions of years, almost any artificial structure would be so weathered, deformed, and altered that it would resemble natural formations in many ways, and conversely, Natural processes can sometimes create formations that appear remarkably regular or geometric. Without finding indisputable artifacts or materials that could not form naturally, we cannot prove artificial origin. But absence of such proof is not proof of absence, especially given that most of Earth's subsurface has never been examined and given that any materials or artifacts from millions of years ago would likely be degraded beyond easy recognition. If the Silent War involved civilizations advanced enough to wage global conflict with devastating weapons, they certainly would have had the technology to build underground, to mine, to create tunnel networks and subterranean installations, and some of these might have survived in fragmentary form, might exist today as puzzling anomalies that we glimpse occasionally but do not understand. The hypothetical combatants in a global war might have moved crucial installations underground to protect them from attack, might have built deep bunkers and command centers, might have excavated vast mines to extract resources needed for their war effort, and all of this activity would leave marks in the geology, marks that would persist even after millions of years. Another aspect of subsurface anomalies involves the distribution of certain mineral deposits and concentrations of elements that are difficult to explain purely through natural geological processes. Mining operations occasionally encounter veins or pockets of minerals in configurations that puzzle geologists, formations that seem to require highly specific conditions that should not exist in the locations and depths where they are found. There are scattered reports of metallic objects or alloys discovered embedded in solid rock at depths where they should not exist if they are recent contamination, though many of these reports are poorly documented and difficult to verify. Science progresses through careful documentation and replication, and anomalies that cannot be verified or replicated eventually fade from consideration. Though the occasional well-documented anomaly continues to puzzle researchers who encounter it, continues to sit uncomfortably in the back of scientific literature, neither explained satisfactorily nor given the attention needed to fully investigate it. As you relax more deeply and feel the pull of sleep approaching, imagine the vast hidden world beneath your feet, kilometers of rock holding secrets that we have barely begun to explore, structures and tunnels and anomalies that might be nothing more than geology's random artistry, or might be the remaining fragments of a past we have not yet recognized. The earth beneath us is not merely a solid foundation, but a layered archive, and like any archive, most of its contents remain uncatalogued and unread, waiting for patient investigators to uncover and interpret them. Throughout the history of archaeology and paleontology, there have been occasional discoveries of objects that do not fit comfortably into the established timeline of human technological development, or that appear in geological contexts where they should not exist. Most of these so-called out-of-place artifacts, or OP-arts, have been explained as misidentifications, hoaxes, or misunderstandings of geological context, and skepticism about such claims is entirely appropriate, given how often extraordinary claims have turned out to have mundane explanations. However, a small number of anomalous finds have never been satisfactorily explained and continue to puzzle researchers who study them carefully. These objects exist in museums, in private collections, in scientific papers that remain obscure, and while they do not constitute proof of pre-human civilizations, they do represent data points that do not quite fit the standard narrative and that deserve consideration in any comprehensive attempt to understand Earth's hidden history. The challenge with evaluating such artifacts is that proper archaeological context is crucial, and many of the most interesting anomalies were discovered before modern archaeological methods were developed, or were found by non-specialists who did not recognize the importance of careful documentation. An object without clear context is almost impossible to interpret definitively, but that does not mean we should ignore it entirely, only that we must be cautious in drawing conclusions from it. One category of anomalous artifacts involves objects that appear to show signs of machining or manufacturing found in contexts where such technology should not exist. There are scattered reports of metal objects, including screws, nails, and more complex shaped pieces, discovered embedded in coal or in rock formations that are millions of years old, far older than human civilization and in most cases older than the existence of primates or even mammals. Coal forms from plant material compressed over millions of years, typically dating from the Carboniferous period roughly 300 million years ago. So any object found genuinely embedded within a coal seam, rather than simply mixed in during mining, would have to be at least as old as the coal itself. Several such objects have been reported over the past 2 centuries, mostly by miners who encountered them and reported them to local scientists or newspapers, but very few were preserved and studied carefully, and the provenance of most is difficult to verify. Skeptics rightly point out that objects can become embedded in coal or rock through various means after those materials were extracted, that miners may have been mistaken about where exactly they found objects, and that without careful documentation and analysis, such claims remain anecdotal. Nevertheless, the sheer number of such reports, scattered across different times and locations, suggests that at least some may represent genuine anomalies deserving of further investigation. Among the better documented cases are several metallic objects held in museum collections that have undergone some scientific analysis. The wolf's egg iron, discovered in Austria in 1865, embedded in coal dating to the Tertiary period, is a roughly cube-shaped piece of iron that some have argued shows evidence of machining, though others contend it is a natural formation or possibly a piece of meteoric iron that became embedded in the coal seam through some geological process. The London hammer, found in Texas in 1934, encased in rock claimed to be from the Cretaceous period, consists of an iron hammerhead with a wooden handle. Though analysis of the rock matrix has been disputed, and skeptics argue that the rock formation around the hammer is likely a relatively recent concretion rather than ancient sedimentary rock, the Dorchester pot, a metallic bell-shaped vessel reportedly blasted out of solid rock in Massachusetts in 1851, was said to be embedded in rock from the Precambrian period over 600 million years old, though the object itself has been lost and modern researchers cannot examine it to verify the original reports. These and similar objects exist in a frustrating grey zone, where the reports are sufficiently detailed to be intriguing, but insufficiently documented by modern standards to be conclusive, and where the objects themselves, when they survive, are ambiguous enough that specialists can argue about their origin and nature without reaching consensus. Another intriguing category of anomalous evidence involves what might be described as ancient technology or knowledge that appears earlier than conventional chronology suggests it should. Ancient batteries like the Baghdad battery, ancient astronomical knowledge encoded in monuments and artifacts from early civilizations, ancient maps that appear to show coastlines with remarkable accuracy that should not be possible with the surveying technology available at the time, ancient megalithic structures built with precision that challenges our assumptions about the capabilities of pre-industrial peoples. Most of these examples come from historical rather than pre-human time periods, and therefore do not directly relate to the silent war hypothesis, but they do establish a pattern that human technological history may be more complex and non-linear than simple narratives of steady progress suggest, and they remind us that sophisticated knowledge and capability can arise in unexpected contexts and can be lost when civilizations collapse. If human history over just a few thousand years shows such complexity and such cycles of rise and fall, how much more complex might the history of life on Earth be when considered over hundreds of millions of years? The principle that guides our exploration tonight is that intelligence, once it arises, tends to develop technology, tends to manipulate its environment, tends to leave marks. And if intelligence arose on Earth long before humanity, those marks should exist somewhere, somehow, preserved against the patient grinding of geological time. Some researchers have pointed to certain patterns in the fossil record as potentially representing technological artifacts, rather than biological remains, though this interpretation is highly speculative and not widely accepted. Trace fossils, which are preserved evidence of biological activity rather than body parts, include burrows, tracks, and other marks left by ancient organisms. And the vast majority of these are clearly biological in origin, but occasionally trace fossils are found that show patterns difficult to attribute to known biological behaviours. Straight parallel grooves in rock surfaces from hundreds of millions of years ago might be tool marks or might be scratch marks from some unknown organism, or might be entirely geological features. The boundary between biological, geological, and technological is not always as clear as we might wish, especially when dealing with fragmentary evidence from deep time. As you drift closer to the threshold of sleep, let your mind wander among these ambiguous objects and puzzling patterns, these artifacts that might be nothing or might be everything, these clues that sit on the edge of provability and challenge us to look more carefully, to think more expansively, to consider possibilities that conventional frameworks dismiss. The anomalous artifacts do not prove the silent war, but they suggest that Earth's history contains mysteries we have not yet solved, objects that do not quite fit, pieces of a puzzle we have not yet assembled because we are still missing too many other pieces to see the full picture. Life on Earth has endured through billions of years, adapting to changing conditions, diversifying into millions of species, filling every available niche, but that continuity has been punctuated by moments of catastrophic destruction when vast numbers of species vanished in what we call mass extinction events. The fossil record clearly shows 5 major mass extinctions and numerous smaller ones over the past 500 million years, since complex multicellular life became abundant enough to leave extensive fossils. These extinction events have been extensively studied by paleontologists, and each has been explained through various combinations of volcanic eruptions, asteroid impacts, climate change, ocean chemistry alterations, and ecological cascades. The conventional explanations are well supported by evidence and have been refined through decades of research. Yet when we examine the extinction patterns very carefully, when we look not just at which species died, but also at how they died, and when and in what order, we begin to see patterns that are difficult to explain through random catastrophes alone. Some extinctions show a selectivity, a targeting of specific groups of organisms, while sparing closely related groups, that seems almost purposeful. Some show geographical patterns of survival and death that are hard to attribute to global catastrophes that should affect all regions somewhat equally. Some show timing and progression that suggests multiple waves of destruction rather than single catastrophic events. These patterns might still be explained through complex natural mechanisms, but they also raise the possibility of something else, some additional factor that has not been adequately considered in conventional models. The Permian-Triassic extinction, which we have already discussed, is the most severe known extinction event, but it is not the only one that shows puzzling characteristics. The Ordovician-Silurian extinction approximately 440 million years ago saw about 85% of species disappear in 2 pulses separated by perhaps a million years. And while glaciation and climate change are the favoured explanations, the precise mechanisms in the 2-pulse pattern remain somewhat puzzling. The late Devonian extinctions, actually a series of pulses over several million years around 370 million years ago, primarily affected marine life and have been attributed to ocean anoxia and climate cooling. But the repeated pulsing of extinction over an extended period is curious and might suggest repeated stresses or events rather than a single catastrophe. The Triassic-Jurassic extinction about 200 million years ago eliminated many large terrestrial vertebrates and marine reptiles and has been linked to volcanic eruptions and climate change. But again, the selectivity of which groups died and which survived shows patterns that are not entirely explained by environmental stress alone. The Cretaceous-Palagine extinction 66 million years ago, famous for ending the age of dinosaurs, B is perhaps the best understood and has very strong evidence for an asteroid impact at Chicxulub in Mexico, combined with massive volcanic eruptions in India's Deccan Traps. Yet even this event shows some curious patterns in what survived and what died that paleontologists continue to puzzle over. When we map these extinction events not just in time but also in space, looking at which geographical regions were most severely affected and which retained the highest diversity of surviving species, we sometimes see patterns that are difficult to reconcile with global catastrophes alone. For example, if a massive volcanic eruption or asteroid impact causes global environmental collapse, we would expect the effects to be somewhat proportional to distance from the event, with the most severe impacts closest to the source and gradually diminishing effects further away, modified by factors like prevailing winds and ocean currents. What we actually observe in some extinction events is a more patchy pattern, with some regions very far from proposed impact sites or volcanic provinces being devastated, while other regions closer to the supposed source of catastrophe retain relatively high diversity. This patchiness might be explained through complex ecological factors, through regional differences in climate and ocean circulation, through differences in which species happen to live where and how susceptible they are to various stresses, but it might also be explained if the catastrophe involved multiple sources, multiple events, multiple causes that affected different regions in different ways. A global war using advanced weapons would create exactly such a patchy pattern, with the most severe devastation near the sites of major battles or weapon deployments, and progressively less severe effects in regions more remote from the conflict. The selectivity of extinction also deserves close attention. Why do some groups of organisms go entirely extinct during mass extinction events, while closely related groups survive, sometimes even thriving in the aftermath as they expand into ecological niches left vacant by the extinctions? During the end Permian event, certain groups like trilobites, blastoids, and rugose corals went completely extinct, while other marine invertebrates, including some mollusks and brachiopods, suffered heavy losses but survived, with some species persisting. On land, many groups of reptiles and amphibians went extinct while others survived, and the pattern of which groups died and which lived is difficult to explain purely through ecological factors or environmental tolerances. Some of the victims were highly successful and diverse groups that had dominated their environments for tens of millions of years, while some survivors were relatively minor groups that became dominant only after the extinction. This pattern is consistent with environmental catastrophe combined with some random luck about which species happen to have populations in refugia, where conditions remain tolerable, but it might also be consistent with targeted destruction of specific ecosystems or regions during a conflict, with survival depending partly on whether your habitat was in a battle zone or not. The thought experiment is uncomfortable but worth considering. If you were conducting a war on a global scale with weapons capable of destroying entire regions, the destruction would not be uniform, but would cluster around strategic targets, resource-rich areas, population centers, and the geography of your conflict would determine who died and who survived. Another curious aspect of extinction patterns involves the timing and duration of the extinction events themselves. Some appear to have occurred very rapidly, over thousands of years or even less, while others stretched over hundreds of thousands or millions of years in pulses of heightened extinction rates, interspersed with periods of relative stability. The Permian Triassic extinction is estimated to have taken somewhere between 60,000 and 200,000 years for the main extinction pulse, which is instantaneous geologically but represents thousands of generations for the organisms living through it. Did the environmental catastrophe persist for that entire duration, or were there multiple separate catastrophic events during that period? The rock record lacks the resolution to distinguish between these possibilities in most cases, but where we do have good resolution, we sometimes see evidence of multiple distinct extinction pulses rather than one smooth decline. A prolonged global war, escalating over time and involving multiple destructive events as different weapons were deployed and different battles fought, would create exactly such a pattern of repeated extinction pulses. Alternatively, a single initial catastrophe like massive volcanic eruptions could trigger cascading environmental changes that caused repeated ecological collapses over an extended period. And this is the conventional explanation, but the multi-pulse pattern at least opens the possibility of other interpretations. As you rest and let these ideas wash over you like gentle waves, consider the complexity of extinction, the patterns written in fossils and rocks that tell us which species died and which survived, but that do not tell us directly why or how. The testimony of extinction is a testimony of catastrophe, of Earth being repeatedly stressed to the breaking point, of life clinging to survival through the worst conditions imaginable, and somehow, miraculously, recovering in the aftermath to diversify and flourish again. But extinction patterns also contain hints that not all catastrophes are purely natural, that some might bear the fingerprints of intelligence, of purpose, of conflicts that reshaped the biosphere intentionally or as collateral damage. The silent war, if it occurred, would have driven countless species to extinction, would have devastated ecosystems across the planet, would have left a mark in the fossil record that we might be interpreting as natural disaster when it was actually something far more troubling. The boundary between natural and artificial becomes very blurred when we consider weapons of sufficient power, for such weapons harness and release natural energies and processes, but do so in concentrations and patterns that nature alone would not produce. The extinction testimony is ambiguous, open to interpretation, but it speaks of violence on planetary scales, and that should give us pause as we consider what might have caused it. If advanced civilizations did exist on Earth millions of years ago, and if they engaged in warfare using technologies as advanced relative to their time as our weapons are relative to our time, what signatures would such warfare leave in the geological record? This question requires us to think carefully about what warfare does to an environment, and how those effects might be preserved over vast timescales. Modern warfare leaves obvious immediate devastation, destroyed cities, cratered landscapes, contaminated environments, but it also leaves longer-lasting signatures including radioactive isotopes from nuclear weapons, heavy metal contamination from munitions, chemical pollutants from fuels and explosives, altered landscapes from fortifications and mass graves, and ecological disruption from the destruction of ecosystems. Some of these signatures degrade relatively quickly, but others persist for thousands or even millions of years, and in principle could be detected in ancient rocks if we knew how to look for them and if they were present in the first place. The challenge is that many of the signatures of warfare overlap with signatures of natural catastrophes, making definitive identification extremely difficult without finding explicit artifacts or technologies that have no natural explanation. Nuclear warfare, if it occurred in the ancient past, would leave the most distinctive and long-lasting signatures. Nuclear explosions produce specific isotope ratios that are not naturally occurring, particularly enhanced concentrations of plutonium-244, which does not exist naturally in significant quantities, and which has a half-life of 80 million years, meaning that if it were produced by ancient nuclear weapons, some traces might still remain detectable today depending on initial concentrations. Other fission products have much shorter half-lives and would have completely decayed by now if they were produced more than a few million years ago, but the signature of their decay products might remain in rocks if concentrations were initially very high. The natural nuclear reactors at Oklo in Gabon, which operated about 2 billion years ago, prove that nuclear reactions can occur naturally and leave distinctive isotope signatures that persist for vast durations, so the mere presence of anomalous isotope ratios does not prove artificial nuclear weapons, but the pattern and context of such ratios can provide clues about whether the reactions were natural or artificial. Natural reactors require very specific geological conditions, including uranium ore of sufficient concentration and purity, a neutron moderator like water, and geological stability to allow sustained reactions. If anomalous nuclear signatures appeared in settings where natural reactors should not be possible, that would suggest artificial nuclear activity. Some researchers have pointed to uranium deposits in various locations that show evidence of past fission reactions based on isotope depletion and the presence of fission product residues, but that occur in geological settings where natural reactors seem implausible. The scientific debate about these deposits is highly technical and contentious, with mainstream geologists generally finding natural explanations while a small minority suggest the possibility of artificial origin. The evidence is not conclusive, but it exists, and it includes isotope ratios in some ancient uranium deposits that differ from what natural decay alone should produce, suggesting that fission reactions occurred but in patterns different from the known natural reactors. Additionally, some sedimentary layers from certain time periods show trace concentrations of elements like technetium and promethium that do not occur naturally but are produced as fission products. Though proving that these traces are not contamination from modern nuclear activities or natural cosmic ray interactions is extremely difficult. The presence of what appear to be glassy beads or trinitite-like materials in a few locations, substances that form from melting of sand or rock in nuclear explosions, and that have distinctive structures and compositions, has also been noted. Though again, natural processes like lightning or meteorite impact can produce similar glasses, and distinguishing between these origins is challenging without extensive analysis. Beyond nuclear signatures, a global technological war would likely involve massive resource extraction, industrial processing, large-scale energy generation, and extensive environmental modification, all of which would leave chemical and geological signatures if they occurred on sufficient scale. The mining of metals would concentrate certain elements in specific locations and would leave behind tailings and waste with distinctive chemistry. The smelting and processing of ores would release various pollutants including heavy metals, sulfur compounds, and particulates that would settle into soils and sediments. The burning of fossil fuels or biomass for energy would release carbon isotope and alter carbon isotope ratios in the atmosphere and oceans. The use of certain industrial chemicals would leave molecular signatures that persist in sediments. The construction of large structures would alter landscapes in ways that might remain detectable as unusual geological patterns. The question is whether any of these signatures have been found in rocks from the relevant time periods, and the answer is ambiguous. We do see some chemical anomalies in certain layers that are difficult to explain through natural processes alone, including unusual concentrations of metals, unexpected carbon isotope excursions, and spikes of certain compounds. But in every case, natural explanations can be proposed even if they sometimes seem to require unlikely coincidences or complex combinations of factors. One specific type of signature that would be particularly diagnostic of technological warfare is the presence of synthetic compounds that do not occur naturally, molecules that require industrial processes to create and that are not produced by any known biological or geological processes. Modern industrial civilization has created thousands of such synthetic compounds, including plastics, pesticides, pharmaceuticals, and various industrial chemicals, and many of these molecules are quite stable and will persist in the environment for millions of years, providing a clear marker of industrial activity to any future geologists studying our time. If ancient civilizations had advanced chemistry and industry, they too would have created synthetic compounds, perhaps entirely different molecules from the ones we have made, but nonetheless clearly artificial in origin. The challenge is detecting these molecules in ancient rocks, which requires knowing what to look for and having analytical techniques sensitive enough to detect trace concentrations after millions of years of degradation and dilution. Some researchers have looked for complex organic molecules with structures that seem too regular or too specific to be biological or geological, but this work is in very early stages and results are inconclusive. The use of advanced energy weapons beyond nuclear devices is difficult to characterize because we do not know what such weapons might be or what signatures they would leave. But we can reason that any weapon capable of destroying large areas or large numbers of organisms must release enormous amounts of energy. And energy releases leave signatures. Intense heat leaves thermal markers in rocks, including melting, vitrification, thermal metamorphism, and alteration of mineral structures. Intense pressure leaves shock metamorphism, fractured and shattered rocks, and distinctive microscopic features in minerals. Intense radiation of various kinds might leave signatures in the crystal structures of certain minerals or in the chemistry of affected materials. If we find in ancient rocks evidence of intense energy releases that cannot be easily explained by volcanism, impact, or other natural processes, and especially if these energy releases cluster around the times of major extinctions or other evidence of catastrophe, that would be suggestive of possible warfare, even if not conclusive proof. As you sink deeper into the calm darkness of approaching sleep, imagine Earth's surface 250 million years ago. Imagine the flash of weapons beyond our comprehension. Imagine the landscapes melting and vaporizing, leaving marks that we might find today if we look carefully enough. Marks that whisper across vast time about the silent war that nearly destroyed all life. If we entertain the hypothesis that advanced intelligent species existed on Earth millions of years ago and engaged in devastating warfare, the immediate question that arises is, who were they? What were they like? Where did they come from? And what happened to them? This is perhaps the most difficult question to address because we have no direct evidence of the participants themselves. No fossils clearly showing technological species from the relevant time periods. No artifacts definitively demonstrating intelligence and civilization. Only the circumstantial evidence of anomalies and patterns that might be interpreted as signs of ancient conflict. In the absence of direct evidence, we can only speculate, but that speculation can be informed by what we know about evolution, about the deep history of life on Earth, about the possibilities and constraints that biology and physics impose, and about the patterns we do observe in the geological and fossil records. The story of who fought the Silent War is necessarily fragmentary and uncertain, built from hints and guesses, but it is worth considering because it helps us understand what we should be looking for and how we might recognize evidence if we find it. Life on Earth is approximately 3.5 billion years old, beginning with simple single-celled organisms and remaining at that level of complexity for the first several billion years of Earth's history. Multicellular organisms evolved around 600 million years ago, and complex animals with hard body parts appeared in the Cambrian explosion roughly 540 million years ago. From that point forward, life rapidly diversified into an astonishing array of forms, experimenting with different body plans, different ecological strategies, different adaptations to every imaginable environment. Evolution is not directed toward any particular goal, not moving steadily toward greater intelligence or complexity, but rather simply adapting organisms to survive and reproduce in their environments. And intelligence is just one possible adaptation among many. However, intelligence is a particularly powerful adaptation when it does arise, because it allows flexible responses to changing conditions, allows learning and culture, allows manipulation of the environment in sophisticated ways, and therefore, once a species crosses a certain threshold of cognitive capability, it tends to proliferate and dominate because intelligence is useful in almost every ecological context. On Earth, intelligence of various forms has evolved multiple times in different lineages, including octopuses, crows, parrots, dolphins, elephants, and of course primates, demonstrating that evolution can and does produce intelligence when conditions favor it. Given that complex life has existed for over 500 million years, and given that intelligence has evolved multiple times in just the last few tens of millions of years, it seems entirely plausible that intelligence could have evolved at earlier periods as well. perhaps in forms very different from anything alive today, perhaps in lineages that left no descendants or whose descendants lost the intelligence their ancestors possessed. The fossil record is notoriously incomplete. Preserving only a tiny fraction of the species that have existed, and heavily biased toward organisms with hard parts like shells and bones, and toward organisms that lived in environments conducive to fossilization like shallow marine settings, organisms with entirely soft bodies, organisms that lived in upland terrestrial environments where erosion dominates over sedimentation, organisms that existed for relatively brief periods of geological time. All of these are very unlikely to leave fossils that we would ever find. A species that existed for only a few million years during the Permian or Triassic or Carboniferous periods, that had perhaps no hard skeletal parts or only small delicate skeletons, that lived in environments poorly represented in the fossil record, might have existed and gone extinct without leaving any fossils we have yet discovered. This is not special pleading, but simply recognizing the limitations of the fossil record, which paleontologists acknowledge is very incomplete and which undoubtedly contains vast gaps representing creatures that lived and died without leaving traces we can find. If intelligence did evolve in the deep past, what might those intelligent species have been like? We can reasonably assume they would have been complex multicellular organisms of some significant size because intelligence requires nervous systems of sufficient complexity, and building complex nervous systems requires either large neurons or large numbers of neurons, which in turn requires either a large body or an extremely efficient compact nervous system design. They might have been marine organisms, since the oceans have always been rich in life and marine environments offer many opportunities for intelligence to be useful in hunting, escaping predators, and manipulating complex three-dimensional spaces. They might have been terrestrial organisms, since land offers different opportunities including more concentrated energy resources from plants, and the possibility of using fire and manipulating materials in ways difficult in water. They might have had body plans utterly different from any animals alive today, perhaps descended from lineages that went extinct entirely during one of the mass extinctions. Evolution is creative and opportunistic, producing forms that seem bizarre and unlikely yet work perfectly well. And over hundreds of millions of years, evolution has had time to explore vast numbers of possible designs. The key characteristic we care about for this hypothesis is not what they looked like, but whether they could develop technology. And technology requires certain capabilities, including the ability to manipulate objects with precision, the ability to perceive and understand cause and effect, the ability to plan and execute complex sequences of actions, the ability to communicate and transmit knowledge, and the physical resources and environments that make tool use advantageous. Many different types of organisms could potentially meet these criteria. On Earth today, octopuses have remarkable manipulative abilities with their arms, considerable intelligence, and problem-solving skills, yet they have not developed technology, partly because they are marine, have short lifespans, and do not have social structures that allow cumulative cultural transmission of knowledge across generations. If conditions were different, if octopuses lived longer and formed stable social groups, they might be capable of developing technology despite lacking hands. Birds like crows demonstrate sophisticated tool use and problem solving despite lacking hands, using their beaks and feet to manipulate objects. Elephants with their trunks show that appendages very different from human hands can still be used for delicate manipulation. The point is that technology does not require a specific body plan, but rather requires a combination of intelligence, manipulation capability, and social organization that allows knowledge to accumulate across generations. And various different evolutionary paths might lead to these capabilities. If intelligent technological species existed during the Permian period, the time when the Great Dying occurred, they would have evolved from organisms living during the Carboniferous and earlier Permian, a time when life on land was dominated by early reptiles, amphibians, and various arthropods, while the oceans hosted diverse fish, sharks, various invertebrates, and early marine reptiles. Any of these lineages might have produced intelligent descendants given enough time and the right selection pressures. Imagine, for example, a lineage of Permian reptiles that evolved larger brains and more sophisticated forelimbs capable of manipulation, that developed social structures and communication, that began using tools and eventually learned to control fire and work metals. Over the course of several million years, such a species might progress from simple tool use to sophisticated technology, might develop agriculture and cities, might discover metallurgy and chemistry, and eventually achieve industrial civilization. This is not implausible. It is simply a repeat of the path humans took, but occurring tens of millions of years earlier with different creatures. The question is not whether it could happen, but whether it did happen, and that question can only be answered by finding evidence. Evidence that would be very difficult to find after 250 million years of geological processes, but that should exist in principle if the events occurred. Another possibility is that multiple intelligent species evolved at different times, perhaps competing with each other, perhaps engaging in the conflict that we hypothesize as the Silent War. Intelligence is a powerful adaptation, but also a dangerous one, as human history demonstrates. Because intelligent species can develop technologies that threaten their own survival, can overexploit their environments, can engage in conflicts that escalate beyond control. If two or more intelligent species arose during the Permian period, perhaps one terrestrial and one marine, or perhaps two terrestrial species in different regions, they might initially have ignored each other but eventually come into conflict over resources, territory, or simply out of fear and misunderstanding. A war between technological species would be devastating, especially if both sides developed weapons of mass destruction, and such a war might explain a catastrophic extinction at the Permian-Triassic boundary better than volcanism alone. This is highly speculative, but it fits the pattern of evidence better than some might expect, including the rapid and severe extinction, the global distribution of destruction, the chemical and physical anomalies, and the fact that recovery took millions of years, suggesting the environment was not just damaged but poisoned in ways that prevented life from recovering quickly. Let these thoughts drift through your mind as you relax into deeper rest, imagining the alien intelligence that might have gazed at the same stars we see, that might have wondered about their place in the universe, that might have built and dreamed and hoped and feared, and that ultimately perished in a conflict that consumed their world. We will never know their thoughts, never hear their languages, never see their faces, but if the evidence is real, then they were real, and their story deserves to be remembered even if we can only guess at the details. The question of who fought the Silent War remains open, a mystery wrapped in layers of rock and time. But it is a question worth asking because it reminds us that intelligence is precious and fragile, that it arises rarely and can be extinguished, and that the universe cares nothing for our plans and dreams if we destroy ourselves in pursuing them. When we study the Permian-Triassic extinction event in detail, what emerges is a picture of environmental collapse so complete and so prolonged that it is difficult to fully grasp how any life survived at all. The extinction itself appears to have occurred in several pulses over a period of perhaps 60,000 to 200,000 years, which is the blink of an eye in geological terms, but represents countless generations for the organisms experiencing it. The fossil record shows that marine ecosystems were hit first and hardest, with reef systems collapsing entirely, with vast swaths of the ocean floor becoming anoxic dead zones devoid of oxygen and filled with hydrogen sulfide, with the entire ocean circulation system apparently breaking down as temperature gradients that normally drive currents weakened or reversed. On land, forests died, soils eroded away, river systems changed from meandering stable flows to braided streams, indicative of flash flooding and lack of vegetation, to stabilize banks, and vast areas became barren deserts supporting almost no life. The few organisms that survived did so by finding refugia in caves, in high latitudes, in deep ocean trenches, anywhere that conditions remained marginally tolerable. And even these survivors were stressed, showing signs in the fossil record of stunted growth, deformities, and rapid evolution as they adapted desperately to the new hostile conditions. Conventional explanation for this environmental collapse centers on the Siberian traps eruptions releasing massive amounts of carbon dioxide and sulfur dioxide, causing global warming of perhaps 10 to 15 degrees Celsius on top of already warm Permian temperatures, leading to ocean warming and stratification, causing the oceans to lose oxygen, release hydrogen sulfide, acidifying both oceans and rain, triggering cascading ecological collapses as food chains broke down. This explanation is well supported by evidence including the timing of the volcanism matching the extinction, the presence of volcanic ash and aerosols in sediments from this period, geochemical models showing how volcanic emissions could cause the observed environmental changes, and the presence of evidence for ocean anoxia and hydrogen sulfide in the rock record. However, this explanation has always had some difficulties fully accounting for the speed and severity of the collapse. Volcanic eruptions of similar magnitude have occurred at other times in Earth's history, without causing extinction anywhere near as severe. The Siberian traps eruptions were certainly massive and prolonged, but other large igneous provinces, like the Deccan traps in India, did not cause comparable extinction even though they were also enormous volcanic events. Something about the Permian Triassic event was different, more severe, more devastating than volcanism alone seems capable of causing. One additional factor that may have contributed is the configuration of the continents during the Permian period. All the major land masses were joined together in the supercontinent Pangaea, which created extreme continental climates with vast interior deserts, limited coastal regions where marine and terrestrial ecosystems could interact, and ocean circulation patterns that may have been prone to stagnation. The assembly of Pangaea was completed during the late Carboniferous and Permian periods, and this assembly itself caused significant environmental stress as shallow seas that had previously separated continents were eliminated, as climate patterns changed due to the altered geography, and as ecological systems that had been isolated were suddenly brought into contact. A world with one supercontinent is inherently more vulnerable to global catastrophe because there are fewer isolated refugia where species can survive localized disasters, fewer barriers preventing the spread of disasters from one region to another, and less overall environmental diversity to buffer against change. If a disaster occurs in a world of scattered continents, some regions are likely to escape the worst effects, but in a supercontinent, the disaster can sweep across nearly all terrestrial environments without obstacle. If we add to volcanic eruptions an unfavorable continental configuration the hypothesis of technological warfare, the environmental collapse becomes more understandable. A global war using weapons of mass destruction would directly add to the environmental devastation, releasing additional greenhouse gases from fires and explosions, injecting particulates and toxins into the atmosphere, destroying ecosystems directly through blast effects and radiation, and potentially triggering volcanic eruptions through the immense energies released by advanced weapons. The combination of volcanism, warfare, and the continental configuration of Pangaea creates a perfect storm of catastrophe that exceeds any single factor alone. Moreover, warfare would explain some features of the extinction that are difficult to account for with volcanism alone, including the rapidity of the initial extinction pulse, the selectivity of which ecosystems and species were most affected, and the prolonged nature of the recovery suggesting that the environment was not just stressed but actively poisoned by substances that took millions of years to break down or be buried. Nuclear warfare would release long-lived radioactive isotopes that would contaminate environments for millions of years. Chemical warfare might release persistent toxins. Even conventional warfare on a large enough scale would devastate ecosystems and prevent recovery through ongoing destruction and disruption. The evidence from the rock record shows that after the main extinction event, Earth's ecosystems remained impoverished for several million years, showing little diversity and dominated by a few hardy opportunistic species that could tolerate the harsh conditions. This prolonged recovery period is unusual compared to other extinction events, where ecosystem diversity typically begins to recover relatively quickly once environmental conditions stabilize. The delay in recovery after the Permian-Triassic extinction suggests that conditions remained hostile for an extended period, that something was actively preventing ecosystems from recovering, and this pattern is consistent with environmental contamination by substances that degraded only slowly. Coal deposition, which had been common during the Carboniferous and Permian periods, when extensive forests covered much of the land, essentially ceased for several million years after the extinction, indicating that forests did not re-establish during this time. A pattern that might reflect not just harsh climate, but also soil contamination or other factors preventing plant growth. When forests finally did return, they were different from pre-extinction forests, dominated by different groups of plants, suggesting that whatever caused the extinction had permanently altered the conditions for plant life. The ocean showed a similar pattern of prolonged misery and delayed recovery. Reef ecosystems, which had been abundant and diverse during the Permian period, were completely destroyed at the extinction and did not recover to pre-extinction levels of diversity and extent for approximately 10 million years, an extraordinarily long time, suggesting that ocean chemistry or other conditions remained hostile to reef-building organisms for that entire period. The organisms that did survive in the immediate aftermath of the extinction were mostly small, simple species that could tolerate low oxygen, high carbon dioxide, variable temperatures, and generally stressed conditions. These survivor species often show unusual features including small body size, simplified morphology, and evidence of frequent developmental abnormalities, patterns that are consistent with populations living in marginal conditions at the edge of survival, and exposed to mutagenic or teratogenic substances that cause birth defects and developmental problems. If the environment were contaminated with radiation or toxic chemicals from warfare, we would expect exactly these patterns of small stressed populations showing high rates of abnormality and slow recovery. As you rest and let your breathing slow, imagine the desolate world of the early Triassic period, the first few million years after the Permian extinction. Imagine landscapes barren of forests, rivers cutting through naked rock and soil with no vegetation to hold them in place, oceans dim and murky and nearly lifeless except for scattered populations of hardy survivors, skies perhaps tinted strange colours by aerosols and dust, temperatures sweltering, conditions hostile to almost all complex life. Imagine the silence of a world where the vast chorus of living things had been reduced to a whisper, where you could walk for miles without encountering an animal larger than a rat, where the ocean shore was not teeming with life but barren and stinking of sulphur. This was the inheritance left by the Silent War, the world that remained after the conflict burned itself out and the survivors emerged blinking into the wreckage. Life persisted, because life is tenacious and finds ways to survive even the worst catastrophes. But it took millions of years for the planet to heal, for ecosystems to rebuild, for diversity to return. The environmental collapse at the end of the Permian was the most severe crisis life on Earth has ever faced, and the scars of that collapse are written in rocks all over the world, testimony to destruction on a scale almost beyond imagination. After the devastation of the Permian-Triassic extinction, Earth slowly, painfully, began to heal. The early Triassic period, spanning roughly the first 5 million years after the extinction, represents a time of ecological impoverishment and environmental stress, but also a time when the survivors began to diversify and adapt to the changed world. The fossil record from this period shows ecosystems dominated by disaster taxa, opportunistic species that thrive in disturbed conditions but that are typically outcompeted when ecosystems stabilize. On land, the reptile Lystrosaurus became extraordinarily abundant, representing perhaps 95% of terrestrial vertebrate fossils from the earliest Triassic, a level of dominance unprecedented in the fossil record and indicating that few other species were able to compete with this hardy survivor. In the oceans, microbial mats became common on the seafloor in regions where complex ecosystems had existed before, representing a regression to simpler Precambrian style communities because the more complex organisms that normally dominate had been wiped out. These patterns indicate that conditions remained harsh and that ecological complexity could not yet re-establish because the environmental conditions or perhaps contamination prevented it. Gradually, over millions of years, conditions improved. Volcanic activity from the Siberian traps eventually declined. The excess carbon dioxide in the atmosphere was slowly removed through weathering of rocks and burial of organic matter in sediments. Ocean circulation systems re-established themselves as temperature gradients returned to more normal patterns. Oxygen levels in the deep ocean recovered as organic matter stopped raining down from the surface in such overwhelming quantities. If there had been contamination from warfare, the radioactive isotopes decayed, the chemical toxins broke down or were buried under new sediments, and the environment gradually became more hospitable to life. The survivors of the extinction began to diversify, evolving new forms to fill the empty ecological niches left by the millions of extinct species. This process of adaptive radiation is a common pattern after mass extinctions, with the surviving lineages rapidly evolving to exploit available resources and ecological opportunities. But the pace of radiation after the Permian-Triassic extinction was slower than after other extinctions, again suggesting that conditions remained marginal for an extended period. By the Middle Triassic period, roughly 10 to 15 million years after the extinction, ecosystems had recovered much of their complexity and diversity, though the species and even the major groups were often different from those that had dominated before. On land, new groups of reptiles called archosaurs began to diversify, eventually giving rise to dinosaurs, pterosaurs, and crocodilians, groups that would dominate terrestrial ecosystems for the next 150 million years. The cynodonts, a group of mammal-like reptiles that survived the extinction, gave rise eventually to true mammals, though mammals would remain small and relatively insignificant until after the dinosaurs went extinct 66 million years ago. In the oceans, new groups of marine reptiles, including ichthyosaurs and plesiosaurs, evolved and radiated, filling niches left vacant by the extinction of earlier marine reptiles. Reefs began to recover, initially built by different organisms than Permian reefs, but gradually becoming more diverse and extensive. The recovery of Earth's ecosystems after the Great Dying is a testament to the resilience of life, to its ability to persist through even the most catastrophic conditions, and to rebuild complexity and diversity given enough time. The renewed world of the Triassic period was in some ways similar to the Permian world that had come before, with continents still assembled into the supercontinent Pangaea, with warm climates and high sea levels, with diverse terrestrial and marine ecosystems, but it was also different in fundamental ways, with different groups of organisms dominating, with different ecological structures, with a changed atmosphere and ocean chemistry reflecting the long period of stress and recovery. The dinosaurs that rose to dominance during the late Triassic and Jurassic periods were descendants of small, unassuming archosaurs that had survived the Permian extinction, and their success over the next 150 million years shaped the subsequent history of life on Earth. Mammals, also survivors of the Permian extinction, remained small and mostly nocturnal, a relatively minor group overshadowed by dinosaurs until the end Cretaceous extinction 66 million years ago removed the dinosaurs and opened the way for mammalian radiation. Humans are descendants of those early mammals, and our entire evolutionary lineage owes its existence to the fact that some small furry creatures managed to survive the Great Dying and find a place in the recovering ecosystems of the Triassic. In this sense, we are children of the silent war, descendants of the survivors. shaped by events that occurred more than 200 million years before our species existed. If the Permian extinction had been even slightly more severe, if a few more species had died, if conditions had remained hostile for a bit longer, the recovery might have failed entirely, and Earth might have been left a barren world like Mars with only microbial life persisting in a few marginal environments. The fact that complex life survived and recovered and eventually produced mammals and primates and humans is a testament to the resilience of life, but also a reminder of how close we came to not existing at all, how precarious the thread is that connects us to the deep past. Every human who has ever lived owes their existence to the survival of a few hardy creatures during the worst environmental catastrophe in Earth's history. And if that catastrophe was partly or wholly the result of an ancient war, then we carry within our very existence a warning about the dangers of technological intelligence unconstrained by wisdom. As you drift deeper towards sleep, let the story of recovery wash over you. Let the images of a wounded planet slowly healing fill your thoughts, forest returning, oceans clearing, life diversifying once more into the endless forms most beautiful and wonderful. The silent war ended not with victory for either side, but with exhaustion and devastation, with a world so damaged that neither the victors nor the vanquished could continue. And in that silence, life began again, patiently rebuilding what had been destroyed, filling the emptiness with new experiments, new forms, new possibilities. The recovery took millions of years, timescales so vast that human minds struggle to grasp them, but it happened, and the result is the living world we know today, with all its diversity and beauty and complexity. We are part of that recovery, part of the long chain of life that survived and persisted and adapted, and that knowledge should give us both humility and hope. Humility because we recognize how easily it all might have been lost, and hope because we see that even from the worst devastation, life can return. While the Permian-Triassic extinction is the most severe, and therefore the most likely candidate for an event influenced by warfare, it is not the only extinction event that shows anomalous features or patterns that might warrant closer examination. Earth's fossil record reveals 5 major mass extinction events over the past 500 million years, along with numerous smaller extinction pulses that eliminated significant fractions of species without qualifying as major mass extinctions. Each of these events has been studied extensively by paleontologists and geologists, and each has mainstream explanations involving volcanic eruptions, asteroid impacts, climate change, ocean chemistry changes, or combinations of these factors. The mainstream explanations are well supported by evidence and should not be dismissed, but when we look for patterns that might indicate something beyond natural disasters, when we look specifically for signatures that could suggest technological warfare or other intelligent intervention, we find that several extinction events show at least some features that could potentially be interpreted through such a lens if we are willing to entertain the possibility. The Ordovician Silurian extinction, which occurred in 2 main pulses, approximately 445 and 443 million years ago, eliminated about 80 to 5% of marine species and was particularly devastating to marine invertebrates and reef-building organisms. The standard explanation involves a period of glaciation, followed by rapid deglaciation, causing sea level changes and climate shifts that stressed marine ecosystems, combined with possible ocean anoxia and changes in ocean chemistry. This explanation fits much of the evidence, but the 2-pulse nature of the extinction is somewhat puzzling, with the first pulse associated with glaciation and cooling, followed by a brief recovery, then a second pulse associated with warming and deglaciation. Some researchers have suggested that an asteroid impact or gamma ray burst from a nearby supernova might have contributed to the extinction by damaging Earth's ozone layer and exposing surface life to increased ultraviolet radiation. But evidence for these hypotheses is limited. Could the 2 pulses represent 2 phases of a conflict, or an initial attack followed by a counterattack, or the deployment of different weapons at different times. This is highly speculative, but the pattern of two distinct extinction pulses separated by a brief period of partial recovery is at least consistent with multiple discrete catastrophic events rather than a single drawn-out environmental crisis. The late Devonian extinctions occurred as a series of pulses over a period of several million years, centered around 375 million years ago, and primarily affected marine life, particularly reef ecosystems and certain groups of fish and invertebrates. These extinctions have been attributed to a combination of factors including climate cooling, sea level changes, ocean anoxia, and possibly asteroid impacts, but the cause remains somewhat unclear, and the protracted nature of the extinctions over several million years with multiple pulses is unusual. The pulsed nature suggests that whatever caused the extinctions recurred multiple times rather than being a single event or a smoothly changing environmental condition, and this pattern could be consistent with repeated conflicts or with multiple deployments of devastating weapons over an extended period of warfare. Again, this is speculative, but the pattern at least does not rule out such an interpretation. The Triassic-Jurassic extinction approximately 200 million years ago marked the transition between the Triassic and Jurassic periods and eliminated about 75% of species, including many large terrestrial vertebrates and various marine groups. This extinction opened the way for dinosaurs to become the dominant land animals, replacing the various other reptile groups that had dominated during the Triassic. The cause is attributed to volcanic eruptions associated with the breakup of Pangaea, specifically the Central Atlantic magmatic province, which released vast quantities of carbon dioxide and caused rapid climate change. The extinction appears to have been relatively rapid, occurring over perhaps a few tens of thousands of years, and shows patterns similar to other extinction events associated with large igneous provinces. Some researchers have noted that the extinction was selective in ways that are difficult to fully explain through environmental stress alone, with some groups going entirely extinct while closely related groups survived and thrived. Could there have been a second, less severe episode of warfare at this time? Perhaps remnants of factions from earlier conflicts, or a new intelligence arising and coming into conflict with existing groups? There is no clear evidence for this, but the possibility exists. The Cretaceous-Paleogene extinction 66 million years ago is famous for ending the age of dinosaurs, and is the best understood of all mass extinctions thanks to excellent preservation of the boundary layer in many locations and to the unambiguous evidence of the Chicxulub asteroid impact in Mexico. The connection between the asteroid impact and the extinction is very strong, supported by global distribution of impact ejecta, shocked quartz iridium anomalies, and the presence of the impact crater itself. However, even this extinction has some complexities, including the fact that massive volcanic eruptions in India's Deccan Traps were also occurring at the same time and may have contributed to the extinction, and the fact that the pattern of which groups survived and which died is not entirely explained by the immediate effects of the impact. The extinction eliminated non-avian dinosaurs, pterosaurs, marine reptiles, ammonites, and many other groups, while sparing birds, mammals, crocodilians, turtles, and many marine organisms. This pattern is generally explained through ecological factors and chance, but it shows that even when we have a clear cause like an asteroid impact, the details of extinction are complex and not fully predictable. For the purposes of our hypothesis about pre-human warfare, the Cretaceous extinction is probably the least likely to involve anything beyond natural causes, because it is so well explained by the asteroid impact, and because it occurs relatively recently in geological time, after dinosaurs had ruled for over 100 million years, making it unlikely that other intelligent species were involved. The pattern that emerges when we survey all the major extinction events is that each involves a combination of rapid environmental change, often involving volcanism or impacts combined with complex ecological responses that cascade through ecosystems causing widespread death. Most or all of these extinctions can be explained adequately through natural processes without invoking warfare or other intelligent causes, but several of them, particularly the Permian-Triassic extinction and possibly the Ordovician, Silurian and late Devonian events, show patterns of multiple pulses, unusual chemical signatures and selectivity of extinction that could potentially be consistent with warfare if such occurred. The key point is not that we can prove warfare caused these extinctions, but rather that we cannot rule it out based on available evidence, and that some features of the extinction patterns are at least consistent with the hypothesis, and might warrant more detailed investigation looking specifically for signatures that could distinguish natural from artificial causes. As you rest, let your mind wander through these multiple catastrophes scattered through Earth's history. Imagine the resilience of life that has survived them all. Imagine the possibility that some might have been not just bad luck, but the result of intelligence destroying itself. And consider what that possibility means for us today as we develop ever more powerful technologies. One of the strongest arguments against the hypothesis of pre-human intelligence on Earth is the apparent absence of fossils clearly showing intelligent technological species from the relevant time periods. If intelligent species existed millions of years ago, we should be able to find fossils of them, the argument goes, just as we find fossils of dinosaurs and ancient mammals and countless other extinct organisms. The fact that we have not found such fossils seems to argue strongly against their existence. However, this argument is less conclusive than it might first appear, because it underestimates how incomplete the fossil record is, and how difficult it would be to recognize evidence of ancient intelligence, even if we found it. The fossil record is extraordinarily biased towards certain types of organisms in certain types of environments, and the vast majority of species that have ever lived left no fossils at all. Fossilization requires very specific conditions, typically involving rapid burial in sediments in aquatic environments where decay is slowed and where minerals can infiltrate tissues and preserve their structures. Organisms with hard parts like shells, bones and teeth fossilize much more readily than soft-bodied organisms. Organisms that live in lowland, aquatic or near-aquatic environments fossilize more readily than those living in upland, terrestrial environments where erosion dominates. Organisms that are abundant and widespread are more likely to leave fossils than those that are rare or restricted to small areas. And even when fossils form, they must survive millions of years of geological processes without being destroyed by heat, pressure, erosion, or subduction before we have any chance of finding them. These biases mean that the fossil record preserves only a tiny skewed sample of past life, and the older the time period, the less complete the record becomes because more time has passed for geological processes to destroy fossils. For the Permian period, 250 million years ago, the fossil record preserves representatives of many major groups of organisms, and gives us a general picture of what ecosystems were like, but it is certainly not complete. There are many gaps, many groups that we know existed but that are represented by only a few fossils, many time intervals and geographical regions where we have very few fossils at all. If an intelligent species existed during the Permian, whether we would find fossils of it would depend on many factors, including how abundant it was, where it lived, whether it had hard skeletal parts, how long it existed before going extinct, and simply on luck of whether the right rocks happened to be exposed in places where paleontologists have looked. A species that existed for only a few million years during the Permian, that was never particularly abundant, that lived primarily in upland environments away from areas of active sedimentation, and that perhaps had a lightly built skeleton or even no skeleton at all, might leave no recognizable fossils, despite having been real and despite having developed civilization and technology. Moreover, even if fossils of such a species did exist, would we recognize them as representing intelligent technological organisms? Intelligence does not leave obvious marks on skeletal anatomy, unless it is associated with very large brain size relative to body size, and brain tissue itself does not fossilize, so we can only infer brain size from the internal volume of the skull. Many intelligent organisms, including octopuses and some birds, have relatively modest brain sizes by absolute volume and achieve intelligence through efficiency rather than size, so even finding fossils with unusually large brain cases would not be conclusive evidence of intelligence. Tool use and technology also do not leave obvious marks on bones unless they involve very specific repetitive motions that create characteristic wear patterns as seen in some fossils of early humans showing skeletal modifications associated with habitual tool use. A species that used tools primarily for mental tasks, that had advanced technology, that perhaps even had prosthetic enhancements or technological extensions of their bodies, might leave skeletons that look unremarkable to paleontologists who do not know what to look for. The context of fossils is also crucial, but if a species was fossilized in isolation rather than in association with artifacts or structures, we would have no way of recognizing that it was intelligent just from the bones. There is also the possibility that intelligent species, if they existed, might have actively avoided leaving fossil evidence, either intentionally through burial practices that prevented fossilization or simply as a side effect of living in ways that did not lead to fossilization. Modern humans are unlikely to fossilize in large numbers because we typically either bury our dead in ways that promote decay rather than preservation, or cremate them, and we live primarily in terrestrial environments where erosion is common and sedimentation rare. If our civilization were to vanish today, future paleontologists would find very few human fossils despite our species numbering billions of individuals, because the conditions for fossilization are rare. An advanced species might deliberately destroy or dispose of their dead in ways that prevented fossilization for cultural or practical reasons, and we would then find almost no trace of them in the fossil record, no matter how abundant they had been. The absence of fossils therefore tells us much less than we might hope about what actually existed in the past. There have been occasional reports of anomalous fossils, unusual specimens that seem to show features difficult to explain through conventional paleontology, but most of these have been explained as misidentifications, unusual preservation, or simply natural variation, and the few that remain puzzling are typically dismissed as insufficiently documented or too ambiguous to draw conclusions from. The scientific process rightly demands strong evidence for extraordinary claims, and a single anomalous fossil is not strong evidence unless it can be studied thoroughly, replicated, and verified. However, this conservative approach, while scientifically sound, might also cause us to overlook genuine anomalies that do not fit our expectations. If fossils of intelligent species from the deep past do exist in museum collections, they might be catalogued as unusual specimens of known groups, might be sitting unstudied in storage, might have been dismissed as malformed or poorly preserved examples of more familiar organisms. The history of paleontology includes numerous examples of fossils that were initially misinterpreted or overlooked, and only later recognized as representing important new species or groups, so the possibility that something significant has been missed remains open. As your breathing slows and you drift towards sleep, imagine the vast cemeteries of stone where ancient bones lie waiting. Imagine the countless species that lived and died, leaving no trace except perhaps a single fragment of bone in a remote outcrop somewhere. Imagine the silence of all those missing fossils, all those organisms that existed but that we will never know because the conditions were not right for their preservation, or because we have not yet looked in the right places, or because we looked but did not recognize what we were seeing. The silence of missing fossils is not evidence of absence, but simply absence of evidence, a gap in our knowledge that may or may not conceal profound mysteries. The possibility that intelligent species lived and died millions of years ago and left no fossils we have yet recognized remains open. Unlikely perhaps, but not impossible, and that small possibility is enough to keep the hypothesis of the Silent War alive. If we grant for the sake of argument that intelligent technological species existed on Earth millions of years ago and that they engaged in a devastating war, we must ask what could motivate such a conflict, and whether the motivations we infer are plausible. Human history provides ample evidence that intelligent species are capable of warfare, often for reasons that seem tragically irrational in hindsight. But there are patterns to human conflicts that might give us insight into what ancient conflicts might have been about. Wars are typically fought over resources, territory, ideology, fear, revenge, or combinations of these factors. Resources include anything needed for survival or prosperity, such as food, water, energy, materials for technology, and living space. Territory is closely related to resources, but also involves strategic positioning, defensibility, and sometimes symbolic or cultural significance. Ideology includes religious beliefs, political systems, cultural values, and any other ideas that groups consider important enough to fight over. Fear drives conflicts when groups perceive others as threats to their survival or way of life, even if the threat is more imagined than real. Revenge perpetuates conflicts that might otherwise end, as each side seeks retribution for past injuries, creating cycles of violence that escalate over time. These motivations are universal enough that we might expect them to apply to any intelligent species, not just humans, because they arise from basic features of being alive, conscious and social. If two or more intelligent species coexisted on Earth during the Permian period, they might initially have had little contact, occupying different geographical regions or different ecological niches such as land versus ocean. However, as populations grew and technology advanced, they would eventually encounter each other, and that encounter might have been peaceful or might have led to conflict, depending on their natures and their needs. Competition for resources is perhaps the most straightforward motivation for conflict, especially if both species required similar resources, such as land, metals, energy sources, or other materials for their technologies. If both species developed industrial civilization, they would have needed vast quantities of resources, and if key resources were limited or concentrated in specific locations, conflict over access to those resources might have been inevitable. The Permian world was a single supercontinent Pangaea, meaning that there were fewer geographical barriers to expansion and contact than there would be in a world of scattered continents, and this configuration might have made conflict more likely as expanding civilizations inevitably encountered each other. Ideological or cultural differences might also drive conflict, especially if the species involved had fundamentally different values, behaviors, or ways of understanding the world. Humans have fought wars over relatively minor differences in religious interpretation or political philosophy, so it is easy to imagine that species with entirely different biologies and evolutionary histories might find each other fundamentally incomprehensible or threatening. Fear and misunderstanding often play large roles in conflicts, even among humans who are all members of the same species, and who could, in principle, communicate and empathize with each other. So how much greater would fear and misunderstanding be between species that evolved separately and might have entirely different forms of communication, social organization, and thought processes? Even if both sides wanted peace, achieving it might be extremely difficult if they could not understand each other's intentions or if they interpreted each other's actions in threatening ways. The development of weapons of mass destruction would have made any conflict far more dangerous and potentially uncontrollable, a pattern we see clearly in human history with the development of nuclear weapons. Once both sides in a conflict possess weapons capable of causing catastrophic destruction, the logic of deterrence is supposed to prevent war by making it too costly. But deterrence only works if both sides are rational actors who accurately perceive threats and who can communicate their intentions clearly. If misunderstanding, miscalculation, or simple accident occurs, deterrence can fail catastrophically, leading to escalation that neither side intended but that neither can stop once it begins. The Cold War between the United States and Soviet Union came frighteningly close to nuclear war on several occasions due to miscommunications, technical failures and misperceptions, and only luck and the restraint of a few individuals prevented catastrophe. An ancient conflict between non-human species with weapons of mass destruction might not have been so fortunate, especially if the species involved had less capacity for empathy or restraint than humans, or if their communication failures were even more severe than those between human nations. It is also possible that the conflict was not initially global, but escalated over time, starting as a limited dispute over resources or territory, and gradually expanding as both sides mobilized more resources, developed more powerful weapons, and committed more fully to victory. Many human wars have followed this pattern of escalation, with initial optimism that the war will be short and limited, giving way to the reality of prolonged attritional conflict that consumes entire societies and that becomes about survival rather than the original objectives. A war that begins with conventional weapons might escalate to chemical or biological weapons as one side or the other becomes desperate, and from there to nuclear or even more exotic weapons as the conflict threatens the survival of the combatants. By the time both sides realize that they are destroying the planet itself and that neither will survive if the conflict continues, it might be too late to stop, the momentum of war carrying them forward to mutual destruction despite the irrationality of that outcome. Another possibility is that the conflict was not between species, but within a single species, a civil war or ideological struggle that divided a global civilization and led to the deployment of catastrophic weapons against fellow members of the same species. Human history is full of civil wars and internal conflicts that were as destructive as or more destructive than wars between different nations or ethnic groups, and a sufficiently advanced civilization capable of global warfare might tear itself apart over ideological, political, or resource disputes. Such a civil war might explain why recovery after the Permian extinction took so long. If the survivors were scattered remnants of a once unified civilization that had destroyed most of its infrastructure and knowledge in the conflict, and that could not rebuild because the civilization-level organization needed for advanced technology no longer existed, the collapse of a technological civilization back to pre-technological conditions is a real possibility if critical infrastructure is destroyed. And if knowledge is lost, and such a collapse would leave even fewer traces in the geological record than the civilization at its peak would have left. As you let these thoughts drift through your mind, resting comfortably in the darkness, consider the tragic universality of conflict, the way that intelligence and technology can amplify both our capacity to build and our capacity to destroy. The thin line between cooperation and competition that all social species must navigate, and the profound question of whether intelligence inevitably leads to self-destruction or whether wisdom can prevail. The Silent War, if it occurred, was a failure of wisdom, a catastrophe born from the same kinds of motivations that have driven human conflicts, but amplified to planetary scale by technology sufficient to destroy a world. The question of motivation is not whether ancient species would have had reasons to fight, but whether they would have had the wisdom to avoid doing so. And the evidence suggests that if they existed, they lacked that wisdom, or possessed it but failed to apply it in time to prevent catastrophe. If the silent war hypothesis is correct, if advanced intelligent species did exist on Earth and did destroy themselves in a catastrophic conflict that ended with the Permian-Triassic extinction, what legacy did that war leave for the world that followed? The most obvious legacy is the extinction itself, the erasure of 96% of marine species and 70% of terrestrial species, the near total destruction of ecosystems worldwide, and the millions of years required for recovery. This is a legacy of absence, of potential never realized, of evolutionary paths cut off before they could develop, of entire worlds of biology and ecology that might have existed, but that were erased. Every species that went extinct during the Great Dying represented millions of years of evolution, represented unique adaptations and behaviors and ecological relationships, represented potential for future evolution in directions we can only imagine, and all of that was lost in the geological instant. The world that recovered from the extinction was different from the world that existed before, built by different groups of organisms in different configurations, and we cannot know what the world would have been like if the extinction had not occurred. What species might have evolved, what further intelligences might have arisen, what different paths life might have taken. The legacy also includes the physical and chemical changes to Earth's environment that resulted from the war and the extinction. The massive release of carbon dioxide and other greenhouse gases caused long-term warming that persisted for millions of years and that influenced the climate and ecology of the entire Triassic period. The destruction of soil and vegetation led to erosion and changes in sediment deposition patterns that are visible in the rock record. The contamination of the environment with whatever byproducts the war produced, whether radiation, toxins, or other substances, may have influenced the ecology and evolution of the survivors in ways we can only guess at. Mutations caused by radiation or chemical mutagens might have driven some of the evolutionary innovations that appeared in the Triassic, might have accelerated the pace of evolution for some lineages, might have created opportunities for novelty that would not have existed otherwise, though these effects would be very difficult to identify specifically in the fossil record. A more subtle legacy involves the possibilities that were prevented. If the intelligent species that fought the war had not destroyed themselves, if they had instead found a way to resolve their conflicts peacefully, what might they have achieved? With millions of years of additional development, they might have spread beyond Earth, might have developed technologies we cannot imagine, might have transformed themselves and their world in profound ways, might have left descendants that would still exist today alongside the descendants of other Permian survivors. Instead, they are gone, and all their knowledge and achievements are gone with them, leaving only the faintest traces that we struggle to interpret. This is perhaps the most profound tragedy of the Silent War. Not just that so many died, but that so much potential was lost, that an experiment in intelligence and consciousness and civilization was terminated before it could fulfill its possibilities, ended by the very intelligence that made it possible in the first place. The universe is vast and ancient, and intelligence may be rare, each instance precious, and the loss of an intelligent species is the loss of a unique perspective on existence, a unique way of understanding and interacting with reality, gone forever. There is also a legacy for us, the descendants of the survivors, the inheritors of Earth after the war. We exist because certain small creatures survived the Permian extinction, because they adapted to the harsh conditions of the early Triassic, because they diversified and evolved over the next 250 million years, eventually producing primates and humans. Our entire evolutionary history was shaped by the extinction, by the opportunities it created for mammal ancestors, and by the constraints it imposed through the changed environment. If the extinction had been slightly more or slightly less severe, if different groups had survived, or if the recovery had followed a different course, we might not exist, or we might be very different from what we are. In this sense, we are the children of the Silent War, shaped by it even though it occurred unimaginably long ago, carrying within our genes and our history the consequences of events we cannot remember and can barely reconstruct. This should give us perspective on our own conflicts, our own development of weapons of mass destruction, our own capacity for self-destruction. We are not the first intelligence Earth has produced, if the hypothesis is correct, and the first intelligence destroyed itself. Will we be wiser? Will we learn from the evidence written in rocks and extinction patterns? Or will we repeat the tragedy on our own scale, with our own technologies, leaving our own layer of catastrophe for future archaeologists to puzzle over if anything survives to do the puzzling? The legacy of the Silent War is also a legacy of warnings, of evidence that intelligence is dangerous, that technology without wisdom leads to destruction, that the universe does not care about our survival and will not prevent us from destroying ourselves if we choose to do so. The same cognitive abilities that allow us to build civilizations and develop technologies also allow us to build weapons and wage wars, and there may be no escaping this duality, no way to have the benefits of intelligence without the risks. The Fermi paradox asks why, if the universe is so vast and old and likely filled with planets capable of supporting life, we have not detected any signs of other intelligent civilizations, and one possible answer is that intelligence tends to destroy itself before it becomes capable of interstellar communication or travel. Perhaps Earth's deep past provides evidence for this grim possibility. Evidence that the great filter that prevents intelligence from spreading across the universe is not the emergence of life or of intelligence, but the survival of intelligence once it develops technology, and that most or all species fail this test, destroying themselves in wars or environmental catastrophes brought about by their own actions. If this is true, then our survival as a species depends on learning to act with wisdom and restraint, on developing social and political systems that can control and channel our destructive capacities, on recognizing that our technologies give us the power to destroy ourselves, and that we must actively choose not to do so every single day. As you rest, breathing slowly and evenly, let the weight of this legacy settle over you not as a burden but as a call to awareness, a reminder that we are part of something larger than ourselves, part of the long history of life on Earth, inheritors of both the beauties and the tragedies of that history, and responsible for what we do with that inheritance. The silent war, if it occurred, ended in silence because there was no one left to tell the story, no one to remember, no one to mourn. Only the stones and the fossils bearing witness to what had been lost. We have the opportunity to be the ones who remember, who learn, who choose differently, who write a different ending to the story of intelligence on Earth. That opportunity is the greatest legacy of the Silent War, the chance to do better, to be wiser, to survive where others failed, and to carry the light of consciousness and understanding forward into a future that is not written yet, but that we create through our choices. The hypothesis of a pre-human conflict that reshaped Earth, as explored throughout this night's journey, is highly speculative and not accepted by mainstream science, and this fact must be acknowledged clearly and honestly. The scientific method requires that extraordinary claims be supported by extraordinary evidence, that alternative explanations be carefully considered and excluded before accepting radical hypotheses, and that we remain skeptical of ideas that require us to overturn well-established understandings without compelling reason. The conventional explanations for the Permian Triassic extinction and other mass extinction events, explanations involving volcanic eruptions, asteroid impacts and climate change, are well supported by extensive evidence, have been refined through decades of research by thousands of scientists, and should not be dismissed lightly. The anomalies and patterns that we have discussed tonight, the chemical signatures and geological curiosities and extinction patterns that might be interpreted as evidence of warfare, can all be explained through conventional processes, even if those explanations sometimes require complex combinations of factors or unlikely coincidences. The absence of unambiguous fossils of intelligent species, the absence of clear artifacts or technologies from the relevant time periods, and the absence of consensus among scientists studying these issues all argue against the warfare hypothesis and suggest that we should remain skeptical. However, skepticism does not require dismissal, and keeping an open mind to unconventional possibilities is part of good science even when those possibilities seem unlikely. The history of science includes many examples of hypotheses that were initially dismissed as implausible, but that later turned out to be correct once new evidence emerged, or once scientists looked at old evidence with fresh perspectives. Continental drift was ridiculed when first proposed and only accepted after decades of resistance when the mechanism of plate tectonics was discovered and when new data from ocean floor exploration confirmed the hypothesis. Meteorite impacts were considered impossible causes of geological features until overwhelming evidence forced acceptance of impact cratering. The idea that mass extinctions could occur at all was controversial until the fossil record was studied carefully enough to reveal the pattern. Science progresses by entertaining new ideas, testing them against evidence, and revising understanding when the evidence demands it, and this process requires some willingness to consider ideas that challenge conventional wisdom, even when most such challenges turn out to be wrong. The question of whether advanced civilizations could have existed on Earth millions of years ago and left so little trace that we have not yet recognized them definitively is a legitimate scientific question that can be addressed through careful consideration of what evidence should exist and how we might detect it. The Silurian hypothesis paper by Schmidt and Frank explored exactly this question and concluded that while most evidence of an ancient industrial civilization would not survive millions of years, some potential signatures including rapid changes in isotope ratios, increases in synthetic molecules, and rapid warming events associated with extinctions might be detectable and should be looked for systematically. This is good science. Asking what evidence should exist if a hypothesis is true, and then looking for that evidence with appropriate rigor. Some of the signatures they identified do appear in the geological record, particularly at extinction boundaries including the Permian-Triassic event, though whether these signatures require technological civilization or can be adequately explained by volcanism and impacts remains debated. More research looking specifically for these signatures and applying sensitive analytical techniques to rocks from critical time periods would help clarify the question. There are also open questions about the completeness of our understanding of the fossil record and about whether we would necessarily recognize evidence of ancient intelligence if we found it. Paleontology has made enormous progress over the past 2 centuries, but it is still a young science with much left to discover, and new fossil finds regularly surprise researchers by revealing organisms or capabilities that were not expected. The discovery of feathered dinosaurs revolutionized understanding of dinosaur biology and the origin of birds. The discovery of complex trace fossils from very early time periods revealed that animals were behaving in sophisticated ways far earlier than previously thought. The discovery of soft-bodied fossils in exceptional preservation sites, like the Burgess Shale, revealed entire ecosystems of organisms that leave no trace in normal fossil deposits. Each of these discoveries expanded what we thought was possible and reminded us that absence of evidence is not always evidence of absence. The possibility that fossils or other evidence of ancient intelligence exists but has not been recognized remains open, unlikely but not impossible, and worth keeping in mind as new discoveries are made. The philosophical implications of the silent war hypothesis are worth considering even if the hypothesis itself remains unproven, because they bear directly on questions about the nature of intelligence, the long-term survival of technological civilizations, and the responsibilities that come with developing powerful technologies. If intelligence has arisen more than once on Earth, if it has led to technological civilization more than once, and if technological civilization has destroyed itself through warfare or environmental catastrophe more than once, then these patterns tell us something important about the relationship between intelligence and survival. They suggest that intelligence alone is not sufficient for long-term survival, that wisdom and restraint and social cooperation are also necessary, and that species which develop technology without developing the wisdom to control it are unlikely to persist for long on evolutionary timescales. These are sobering lessons, regardless of whether the specific hypothesis of the Silent War is true, because even if pre-human civilizations never existed, we know from our own history that technological civilizations are capable of self-destruction and that nuclear war, environmental collapse, or other catastrophes remain real possibilities that we must actively work to prevent. as you drift in the quiet space between waking and sleeping. Let skepticism and openness coexist in your thoughts. Let the questions remain questions without rushing to answers. Let the mystery be a mystery that invites exploration rather than a problem demanding immediate solution. Science is a process, not a fixed body of knowledge, and the questions we ask today may have different answers tomorrow as new evidence emerges and as our understanding deepens. The silent war may remain forever hypothetical, a story we tell to make sense of patterns in stones and extinctions, or it may one day be confirmed through discoveries we cannot yet imagine. Either way, the exploration is valuable, the questions are worth asking, and the reminder to be humble about what we do not know is always timely. Keep your mind open to possibility while remaining grounded in evidence, and remember that the most important truths are often those that are hardest to prove, but that if true, matter more than anything else. As we drift toward the conclusion of tonight's journey through deep time and hidden history, it is worth reflecting on how the hypothetical silent war of the ancient past echoes in the present, and what parallels exist between that ancient catastrophe and the challenges facing modern humanity. We live in an age of unprecedented technological power, an age when humans have developed weapons capable of destroying civilization and perhaps making Earth uninhabitable for complex life. An age when our industrial activities are changing the planet's climate and causing what some scientists call the sixth mass extinction, as species disappear at rates comparable to some of the great extinctions of the past. These are not distant abstract threats, but present realities that we must confront every day through our choices as individuals and societies. The story of the Silent War, whether it actually occurred or whether it remains a cautionary tale extrapolated from ambiguous evidence, provides a mirror in which we can see our own situation reflected, and the reflection should give us pause. The development of nuclear weapons during the mid-20th century gave humanity for the first time in its history the capacity to cause its own extinction and to render large parts of Earth uninhabitable for thousands of years. The Cold War brought the world repeatedly to the brink of nuclear war, and while we survived that period without catastrophe, the weapons still exist, arsenals still contain thousands of nuclear warheads, and new countries continue to develop nuclear capabilities despite international efforts at non-proliferation. The logic of nuclear deterrence that prevented war during the Cold War is fragile and depends on rational decision-making, clear communications, reliable warning systems, and the absence of accidents or miscalculations. Every time the system has been tested by crises or technical failures, we have been fortunate that cooler heads prevailed and that accidents did not cascade into catastrophe, but there is no guarantee that such fortune will continue indefinitely. The existence of nuclear weapons ensures that a single bad decision, a single failure of communication, a single technical malfunction could lead to escalation that destroys civilization within hours. This is the reality we live with, and it is not so different from what ancient civilizations might have faced if they developed weapons of comparable or even greater power relative to their world. Climate change driven by human industrial activity is already altering Earth's environment in ways that future geologists will be able to detect in the rock record millions of years from now. The rapid increase in atmospheric carbon dioxide from burning fossil fuels, the warming of global temperatures, the acidification of oceans, the melting of ice sheets, the changes in precipitation patterns, and the increase in extreme weather events, all of these are creating a chemical and biological signature that will be preserved in sediments and that will mark our time as a period of rapid anthropogenic change. If current trends continue, the extent of species extinction over the next few centuries could rival that of some of the lesser mass extinctions of the past, and the environmental changes we are causing may take tens or hundreds of thousands of years to reverse, even if we stop emissions immediately. In this sense, we are creating our own extinction event, not through warfare, that through the unintended consequences of technologies we developed for other purposes, and the result may be just as catastrophic as warfare if we do not change course. The parallel to the ancient past is clear. Technological civilizations alter their environments in profound ways, and if those alterations exceed the capacity of ecosystems to adapt, collapse follows. There are also parallels in the political and social challenges of managing dangerous tech. Just as the hypothetical ancient civilizations would have faced the challenge of preventing conflicts from escalating to the use of weapons of mass destruction, we face the challenge of preventing nuclear war and of managing other dangerous technologies, including biological weapons, artificial intelligence, and emerging technologies we have not yet developed but that may be even more dangerous. The difficulty is that technologies developed for beneficial purposes can often be weaponized or can have unforeseen dangerous consequences, and once knowledge exists, it cannot be unknown or uncreated. Nuclear physics was developed partly out of pure scientific curiosity about the nature of matter and energy, but it led directly to nuclear weapons. Biotechnology promises cures for diseases and agricultural improvements, but also enables the creation of engineered pathogens that could be far more deadly than anything nature has produced. Artificial intelligence promises to solve problems and improve lives, but also raises existential questions about control and alignment of goals. The challenge is to develop and use these technologies wisely, to recognize their dangers and regulate them appropriately, and to foster global cooperation rather than competition that leads to arms races and conflicts. The fragility of civilization itself is another parallel between past and present. Modern civilization depends on complex interconnected systems, including power grids, communication networks, supply chains, food production systems, and financial systems, all of which are vulnerable to disruption through natural disasters, technological failures, or malicious attacks. A sufficiently severe disruption to these systems could lead to cascading failures that undermine civilization's ability to function, potentially leading to collapse even without direct destruction through warfare. The resilience of civilization depends not just on the absence of catastrophes, but also on the robustness of the systems that support it, on having backups and redundancies, on maintaining knowledge and skills across distributed populations, and on social cohesion that allows cooperation during crises. Ancient civilizations that destroyed themselves in warfare likely lost the knowledge and infrastructure needed to rebuild, trapping survivors in a post-apocalyptic existence from which recovery might be impossible. We face similar risks if we do not actively work to make our civilization more resilient and sustainable. Yet there is also reason for hope in the parallels between past and present. Life survived the Permian extinction and eventually recovered and diversified into forms more wonderful than what existed before. Intelligence arose again after the destruction of any hypothetical pre-human civilizations, proving that the potential for consciousness and understanding persists even through the worst catastrophes. Humans have shown remarkable capacity for cooperation, compassion, creativity, and wisdom alongside our capacity for destruction, and we have choices about which capacities we cultivate and express. The fact that we can study the past, learn from it, recognize the dangers we face, and choose to act differently is itself cause for hope, because it means we are not doomed to repeat ancient mistakes, but can instead forge new paths based on understanding and wisdom. The story of the Silent War, whether literal history or cautionary metaphor, is ultimately a story about the importance of choices, about the responsibility that comes with intelligence and power, and about the possibility of survival if we choose wisely. As you rest deeply now, breathing slowly and peacefully, let the parallels between ancient and modern resonate in your thoughts without creating anxiety. Let them instead create resolve to be part of the solution, to make choices in your own life that support cooperation rather than conflict, sustainability rather than exploitation. The future is not written, and each of us contributes through our actions and choices to shaping what comes next. The silent war of the past is silent and over, but the choices we make today will echo into the future, just as ancient choices echo to us across millions of years, and we have the opportunity to create echoes of wisdom, peace, and survival, rather than echoes of destruction and loss. The hypothesis of pre-human technological civilizations and ancient warfare remains speculative and unproven, but it has inspired some researchers to look more carefully at evidence that might have been overlooked or misinterpreted in conventional frameworks, and this search continues in various ways across multiple disciplines. Geology and paleontology continue to refine our understanding of mass extinction events, using ever more sophisticated analytical techniques to study the chemistry and timing of extinction boundaries, looking for signatures that might distinguish different types of catastrophes from each other. Advances in geochemistry allow detection of trace elements and isotope ratios at levels of precision and sensitivity that were impossible just decades ago, opening the possibility of finding signatures that previous generations of scientists would have missed. The study of impact structures and of shock metamorphism provides better tools for identifying ancient impacts and distinguishing them from volcanic or other features. The study of ancient climates through proxies preserved in rocks and ice cores gives increasingly detailed pictures of how environments change during critical periods. All of this mainstream scientific work, even though not aimed at proving or disproving the warfare hypothesis, generates data that can be examined from multiple perspectives, including unconventional ones. Some researchers have explicitly called for more systematic searches for evidence of ancient industrial civilizations, arguing that the question is legitimate and that we have the tools to address it if we apply them thoughtfully. The search for so-called technosignatures in the geological record involves looking for chemical, isotopic and mineralogical signatures that would be distinctive products of industrial activity, including synthetic compounds that do not occur naturally, unusual isotope ratios of elements that are produced by industrial processes, concentrations of rare earth elements and metals in patterns that natural processes struggle to explain, and evidence of rapid global environmental changes consistent with industrialization. Some of this work overlaps with the study of the Anthropocene, the proposed geological epoch defined by human impacts on Earth, because understanding what signatures modern industrial civilization is leaving helps us understand what signatures ancient civilizations would have left. If we know what to look for, we can search for those signatures in older rocks systematically rather than relying on chance discoveries. The exploration of Earth's subsurface through deep drilling projects, seismic surveys and mining operations occasionally encounters anomalies that might warrant more careful investigation than they typically receive. Most deep drilling is done for commercial purposes like oil and gas extraction or mineral exploration, and the focus is on finding economically valuable resources rather than on documenting everything encountered along the way. Samples from deep drilling are often stored in core libraries where they remain available for future study, and some researchers have suggested that systematic re-examination of core samples from critical time periods using modern analytical techniques might reveal signatures that were missed in initial studies. The oceans, which cover most of Earth's surface and which are very poorly explored compared to land, also represent a potential source of evidence, with ocean drilling programs collecting sediment cores that preserve detailed records of ocean chemistry and biology over millions of years. The deep ocean floor is where some of the best preserved sediments exist, protected from erosion and weathering, and these sediments may contain evidence of events that left little trace on land. The search for anomalous artifacts continues as well, though with appropriate skepticism given the history of misidentifications and hoaxes in this area. When unusual objects are reported in unusual geological contexts, the appropriate scientific response is careful documentation and analysis, rather than automatic dismissal, because even if 99 out of 100 such reports turn out to be mundane, the one that is genuine could be profoundly important. The challenge is distinguishing signal from noise, real anomalies from misunderstandings, and this requires rigorous methodology, replication, and peer review. Most reports of out-of-place artifacts fail these tests and are explained through conventional means. But the process of testing them is valuable because it refines our understanding of what is possible and what is not, and because it ensures that if a genuinely anomalous artifact does appear, it will be recognized and studied appropriately. There is also growing interest in using modern technology, including artificial intelligence and machine learning, to search for patterns in large datasets that humans might miss. The geological and paleontological literature contains millions of papers describing observations and measurements from locations all over the world, and while individual papers are studied carefully by specialists, the broader patterns across all this data are difficult for any human to grasp comprehensively. Machine learning algorithms can analyze vast amounts of data, looking for correlations, anomalies, and patterns that might point toward interesting phenomena, and some researchers have begun applying these tools to geological and paleontological datasets. Such analyses might reveal patterns suggesting ancient catastrophes, or activities that were not apparent when looking at individual sites or studies. Of course, correlation is not causation, and any patterns identified by machine learning would need to be investigated carefully to determine their meaning, but the tools offer new ways to explore old questions. The search for evidence also includes theoretical work on what signatures should exist and how they might be detected, because understanding what we are looking for is essential to finding it. If ancient nuclear warfare occurred, what isotope ratios would it produce, and how long would they persist? If advanced weapons using exotic physics were deployed, what signatures would they leave in minerals or in the structure of rocks? If industrial-scale mining and processing occurred millions of years ago, what chemical and geological patterns would result? These questions can be explored through modeling and calculation, generating predictions that can then be tested against observations. This is how science works, developing hypotheses that make specific predictions and then checking whether those predictions are borne out by evidence. The warfare hypothesis makes some predictions, including that certain extinction events should show signatures of rapid, high-energy catastrophes beyond what volcanism or impacts alone predict. And these predictions can be tested as our analytical capabilities improve. As you drift peacefully in the gentle darkness of near sleep, imagine the researchers continuing their patient work, studying rocks and fossils, measuring isotopes and elements, drilling cores and examining samples, building models and testing predictions, all in pursuit of understanding what really happened in Earth's deep past. Most of this work confirms conventional explanations and refines our understanding within existing frameworks, but occasionally something unexpected appears, some anomaly that does not quite fit, some pattern that suggests there is more to the story than we thought. These unexpected findings are the treasures of science, the hints that our understanding is incomplete, the invitations to look more carefully and think more deeply. Whether the silent war occurred or not, the search for evidence teaches us about the history of our planet, about the fragility and resilience of life, about the methods and limits of science, and about the importance of remaining curious and open to mystery. The search continues, and perhaps one day the evidence will be clear enough to answer definitively the question of whether we are the first intelligence Earth has nurtured or whether others came before us and left their mark in stone and ash and memory. Throughout this night's journey, we have repeatedly returned to the concept of deep time, and as we approach the end of our exploration, it is worth reflecting more fully on what deep time means and how embracing the perspective of deep time changes how we think about life, intelligence, and our place in the universe. Deep time is more than just an abstract concept of large numbers. It is a fundamental reorientation of how we understand change, how we interpret the world around us, and how we assess the significance of events and actions. When we think in terms of deep time, the timescales of human experience, years and decades and even centuries, shrink to insignificance, and the true immensity of Earth's history becomes apparent. 4.5 billion years is a number too large to grasp intuitively, but we can try by considering that if all of Earth's history were compressed into a single 24-hour day, all of recorded human history would occupy only the last 2 seconds before midnight. The dinosaurs would appear around 10:30 in the evening and vanish at 11:40 in the evening. Complex multicellular life would not appear until perhaps 8 in the evening. The vast majority of Earth's history, roughly the first 16 to 18 hours of our compressed day, would be occupied by microorganisms alone, by bacteria and archaea living in oceans and eventually on land, slowly transforming the planet's atmosphere and surface through their metabolic processes. This perspective is humbling and disorienting because it dethrones humanity from any sense of centrality or inevitability and reveals us as a recent contingent development that occupies the tiniest sliver of time. We are not the pinnacle of evolution, not the inevitable result of progress, not the purpose toward which Earth's history has been building, but rather one experiment among countless millions, one species among billions that have existed. One flash of consciousness in a story that is vastly older and larger than us. This realization could be depressing, could make us feel insignificant and meaningless in the face of such immensity, but it can also be liberating and awe-inspiring. We exist despite impossible odds. We are conscious and capable of understanding and appreciating the universe despite the vast improbability of our existence. And we have the opportunity to create meaning and beauty and knowledge during our brief time, even if that time is fleeting compared to the age of stars and galaxies. The perspective of deep time teaches us to hold our achievements and our struggles with appropriate humility, while still valuing them deeply, to recognize that we matter, even if we are small, and to act with the long view in mind because our actions today ripple forward into futures we cannot see. The silent war hypothesis, if true, provides a cautionary example of what can happen when intelligence arises without the wisdom to manage its power, when the perspective of deep time is lost or ignored in favor of immediate concerns and conflicts. Species that thought in terms of deep time, that recognized its place in the vast sweep of Earth's history and its responsibility to the long future, might make different choices than a species focused only on present conflicts and short-term advantages. The ancient civilizations that we hypothesize fought and destroyed themselves likely thought, as humans often do, that their concerns and conflicts were of paramount importance, that their enemies were existential threats requiring desperate measures, that their immediate survival and victory justified any cost, including the use of weapons that would devastate the world. They could not or did not step back to see themselves from the perspective of deep time, to recognize that their entire civilization was a brief moment in Earth's history, and that destroying the planet to win a war was not victory, but suicide. We face similar choices today, similar temptations to prioritize immediate concerns over long-term consequences. Similar risks of allowing conflicts to escalate beyond the point where they can be controlled. The perspective of deep time offers a corrective, a reminder that what we do today matters not just for ourselves, but for the long future, for the millions of years ahead during which Earth will continue to exist and during which the consequences of our actions will persist. Thinking in deep time also changes how we value the present and how we relate to the natural world around us. Every species alive today is the product of billions of years of evolution, represents a lineage that has survived countless challenges and catastrophes, embodies knowledge and adaptations that have been tested and refined through unimaginable numbers of generations. When a species goes extinct, particularly through human action, we are not just losing that one species, but ending an evolutionary story that stretches back to the origin of life, severing a branch of the tree of life that can never be recovered. The extinctions we are currently causing through habitat destruction, climate change, pollution, and other impacts are erasing evolutionary lineages that survived the Permian extinction and every other crisis over hundreds of millions of years, and they are doing so not out of necessity, but out of carelessness and short-term thinking. From the perspective of deep time, causing extinctions to support a few decades or centuries of human economic growth is monumentally foolish, trading priceless, irreplaceable heritage for temporary gains. The perspective of deep time encourages us to act as stewards of the long future rather than as exploiters of the present. There is also a spiritual or philosophical dimension to deep time, a sense of connection to something much larger than ourselves, a participation in a story that transcends individual lives and civilizations and species. When we hold a fossil and realize that it represents a creature that lived and breathed and struggled to survive hundreds of millions of years ago, when we stand on rocks that formed in ancient oceans long before any animal walked on land, when we look at the night sky and recognize that the light from distant stars has traveled for millions or billions of years to reach our eyes, we are connecting across time with the history of the universe itself. This connection can inspire a sense of wonder and reverence, a recognition that existence itself is remarkable and precious, and a desire to honor and preserve the continuity of life and consciousness. The Silent War, if it happened, was a breaking of that continuity, a severing of evolutionary lineages and civilizations, a moment when the story almost ended permanently. The fact that it did not, that life recovered and continued and eventually produced us, is a gift of almost infinite value, and recognizing that gift should inspire us to avoid repeating ancient mistakes. Let the perspective of deep time settle over you now like a gentle blanket as you drift towards sleep. Let it ease any anxieties about immediate concerns by putting them in the context of vast time. Let it inspire appreciation for the miracle of your own existence and for the existence of all the living world around you. Let it encourage you to think and act with the long view in mind, remembering that we are part of a story much older and longer than ourselves, and that our role is to carry that story forward rather than to end it. Deep time is the ultimate perspective, the view from which we can see ourselves most clearly, and from that view, the importance of wisdom, restraint, and care for the future becomes undeniable. The Silent War may be a story from deep time, but its lessons are for the present, and the choices we make now will echo into deep time, leaving marks that future beings, if any exist, will study and interpret as we study and interpret the marks left by the ancient past. Stories shape how we understand the world, how we interpret our experiences, and how we imagine possibilities beyond what we have directly observed. Throughout human history, myths and legends have preserved cultural memory, encoded wisdom, warned of dangers, and explored the boundaries between the known and the unknown. Many ancient myths speak of ages before the present age, of previous worlds that were destroyed in catastrophes, of wars between gods or titans that reshaped the earth and sky, of ancient wisdom that was lost when civilizations fell. Could some of these myths represent distant, distorted memories of actual events from deep time? Memories so old that their factual basis has been transformed into symbolic or supernatural narratives, but that nonetheless preserve some kernel of truth about the past. This is a controversial question because myths are notoriously difficult to interpret, and because most scholars treat them as cultural constructions rather than as historical records. But the possibility that some myths encode genuine memories of very ancient events deserves consideration, especially when we are exploring hypotheses about pre-human history that would by their nature leave few clear records. Many cultures around the world have flood myths, stories of a great deluge that destroyed the world or nearly destroyed it, and while these myths vary greatly in details, the commonality suggests either that they derive from shared experiences of local floods that were devastating enough to feel world-ending, or that they preserve memory of some larger catastrophe. Perhaps the rapid sea level rise at the end of the last ice age as glaciers melted and flooded coastal regions where humans lived. This is an example of how myth can preserve memory of actual events even while transforming and elaborating them through countless retellings over generations. If myths can preserve memory of events from 10 or 15,000 years ago, the end of the Ice Age, could they preserve even older memories, perhaps passed down through pre-human ancestors or encoded somehow in cultural traditions that stretch back far beyond written history? This seems unlikely because memory degrades and changes with each retelling, and over millions of years any factual basis would be completely lost, transformed beyond recognition. However, if a catastrophe were severe enough, and if its effects persisted for long enough, it might leave marks that are rediscovered by later civilizations, and that inspire myths based on interpreting those marks. For example, if humans or proto-humans encountered unusual geological formations, strange artifacts, or puzzling extinction patterns, and tried to make sense of them, they might create stories to explain what they found, stories of ancient wars or divine conflicts or fallen civilizations. These stories would not be memories of the actual events, but rather interpretive narratives constructed to explain evidence, yet they might still point towards something real, even if their details are entirely mythological. Many of the myths about previous ages and destroyed worlds include elements of fire, flood, darkness, and devastation that echo the actual effects of major extinction events. And while this could be coincidence, or simply the fact that natural disasters are common themes in myth, it is at least interesting that the mythical catastrophes resemble what we find in the geological record. The Greek myth of the Titanomachy, the war between the Titans and the Olympian gods that involved hurling mountains and unleashing cosmic forces, and that reshaped the world, might be interpreted as a distant echo of some catastrophe involving immense energies and global devastation. Though such interpretation is highly speculative and not taken seriously by most scholars, some researchers interested in unconventional history have pointed to myths and legends that they argue contain references to advanced ancient technologies or to non-human intelligences, interpreting these stories as potential evidence of lost civilizations or ancient contact with other species. These interpretations are generally rejected by mainstream scholars who argue that the stories are purely symbolic or that they describe natural phenomena misunderstood by prescientific peoples. And certainly most such interpretations are overly literal readings of texts that were never meant as factual accounts. However, the boundary between myth and memory is not always clear, and dismissing all such interpretations out of hand might cause us to miss genuine insights. A more balanced approach recognizes that myths are primarily cultural and psychological artifacts, products of human imagination and meaning-making, but that they sometimes contain threads of actual memory or observation woven into their symbolic narratives. And teasing apart these threads requires careful analysis that respects both the mythological and the historical dimensions. The role of memory in the silent war hypothesis is necessarily limited because the timescales involved are so vast that no memory could survive from the events themselves. However, if the hypothesis is true, the evidence of those events exists in the rocks and fossils, and humans discovering and interpreting that evidence might create stories and myths that reflect our attempts to understand what happened. In this sense, the present exploration, this documentary journey through deep time and speculative history, is itself a kind of myth-making, an attempt to create a narrative that explains patterns we observe in ways that resonate with our concerns and questions. The difference between this narrative and traditional myths is that it is grounded in scientific evidence and explicitly presented as hypothesis rather than as revelation or tradition. But the underlying impulse is similar: to make sense of the world, to find patterns and meaning, to understand our place in the larger story. Whether the silent war happened or not, thinking about it and exploring the possibility serves functions similar to myth, helping us grapple with questions about intelligence, survival, responsibility, and the future. As you rest comfortably, breathing deeply and evenly, Let the boundary between story and reality blur in that pleasant way that happens as sleep approaches. Let the myths and the science and the speculation blend into a dreamlike narrative that carries you into rest. Stories do not have to be literally true to be valuable, to contain wisdom, to inspire thought and action. The silent war story, whether fact or fiction, contains truths about the dangers of power without wisdom, about the fragility of life and civilization, about the importance of the long view and of making choices with the future in mind. These truths are real and important regardless of the literal historical accuracy of the narrative, and engaging with them through story is one of the ways humans process complex ideas and emotions. Let the story carry you now, let it be a vehicle for rest and reflection, and let its lessons settle into your thoughts not as dogma, but as possibilities to consider, as perspectives to explore, as invitations to wisdom. We have travelled together through a long night's journey into deep time, into the hypothesis of the silent war, into the evidence and speculation and questions that surround the possibility that Earth was once home to intelligent species before humanity, and that those species engaged in a conflict so devastating that it nearly destroyed all life and that it certainly reshaped the planet in permanent ways. We have explored the geological and chemical evidence, the patterns of extinction and recovery, the challenges of deep time, and the limits of the fossil record, the questions of who might have fought and why, the parallels between ancient hypothetical catastrophes and modern realities, and the perspectives and lessons we can draw from this exploration. Now, as we approach the end of our journey and as you drift into the peace of sleep, it is time to gather together the threads of what we have discovered and to reflect on what it all means. The evidence for